Out there in the vast darkness, 61 million light-years away from our own pale blue dot, lies one of the most spectacular and mysterious structures in the entire cosmos, the barred spiral galaxy NGC 1300. Gaze upon its image captured by the Hubble Space Telescope, and you'll witness a breathtaking cosmic whirlpool of starlight, dust lanes, and swirling arms stretching across 130,000 light-years of space. But what makes this galaxy truly extraordinary isn't just its beauty, it's the sheer number of unexplained, strange, and frankly bizarre phenomena unfolding within it that continue to baffle astronomers and challenge everything we thought we knew about how galaxies behave. From inexplicable energy signatures that shouldn't exist to gravitational anomalies that defy the laws of physics as we understand them, NGC 1300 is more than just a pretty picture. It's a cosmic puzzle box waiting to be opened, a place where the normal rules of the universe seem to break down. And in this video, we're not just skimming the surface. We're taking a deep, thrilling journey into the very heart of this distant island of stars to uncover not one, not five, but 30 of the most perplexing and awe-inspiring mysteries that scientists are still struggling to explain. Each of these phenomena tells a story of forces we can't yet measure, of events we can't yet predict, and of secrets the universe is still reluctant to reveal. So if you've ever looked up at the night sky and felt that tug of curiosity, that sense of wonder about what lies beyond our own world, you're in the right place. This isn't just a tour of pretty Hubble images. This is an expedition into the unknown, a chance to walk alongside researchers and explorers as we piece together clues from the farthest reaches of space. By the time we're done, you won't just see NGC 1300 as a distant swirl of light. You'll see it as a living, evolving, and deeply mysterious cosmic entity, one that reminds us just how much we still have to learn about this incredible universe we call home. Our journey into the mysteries of NGC 1300 begins right at its heart, at the very core of the galaxy where we would expect to find a ravenous, energetic beast, a supermassive black hole. And indeed, one is there, an gravitational anchor with a mass millions of times that of our Sun. But here's where the first major puzzle presents itself. Unlike the active, brilliant hearts of many other galaxies which shine with the intense light of superheated matter, the central black hole in NGC 1300 is strangely, almost eerily quiet. It's dormant, it's dim. For a cosmic entity of its size and power, it's putting on a spectacular performance of doing almost nothing at all. And that inactivity is the first clue that something is fundamentally different here. In most galaxies of this type, a supermassive black hole acts like a powerful engine. As it pulls in vast amounts of gas, dust, and even stars, that material doesn't just vanish. It forms a spinning, white-hot disk around the black hole called an accretion disk, which radiates unbelievable amounts of energy across the entire electromagnetic spectrum before the matter finally crosses the point of no return. This process creates what astronomers call an active galactic nucleus, or a GN, one of the most luminous and energetic phenomena in the universe. Yet, when we point our most powerful telescopes at the center of NGC 1300, we don't see that brilliant beacon. We see a faint whisper where we expect a scream. So what could be causing this profound silence? Scientists are actively investigating several compelling theories. One possibility is that this black hole is simply between meals. It might have already consumed the vast majority of the available fuel in its immediate vicinity, entering a temporary period of quiescence, a cosmic hibernation. But the sheer length of time such a phase would last makes this a difficult theory to pin down. Another, more intriguing idea is that the black hole isn't dormant at all, but is instead feeding in a way we can't easily observe. It might be consuming matter in a slow, steady trickle rather than in violent, luminous bursts, a diet so sparse it doesn't generate the intense radiation we typically associate with these monsters. Perhaps the most fascinating theory suggests our view is being blocked. The unique structure of barred spiral galaxies like NGC 1300 features vast lanes of cosmic dust and gas-channeling material inward along the bar. It's possible that this very process is creating a thick, obscuring cocoon around the central black hole, hiding the brilliant accretion disk from our view and allowing only subtle clues of its activity to escape. This wouldn't mean the black hole is quiet. It would mean we're essentially listening to it from outside a soundproofed room. The implications of solving this mystery stretch far beyond this single galaxy. Understanding why this colossal engine is idle helps us piece together the life cycle of supermassive black holes and their relationship with their host galaxies. It challenges our models of how galaxies evolve and how these gravitational behemoths influence the formation of stars and the very structure of the cosmic web around them. This quiet giant in NGC 1300 isn't just a curiosity. It's a question mark written in gravity itself, forcing us to reconsider what we know about the most powerful objects in the universe. But the galaxy's mysteries don't end with its silent heart. As we pull our view back from the center, another enigma emerges, one that is entirely invisible to optical telescopes but screams across the radio wavelengths of the electromagnetic spectrum. Surrounding NGC 1300 are vast, ethereal loops and arcs of radio emissions, colossal structures that weave through the galaxy's halo like ghostly halos. These aren't mere wisps, they are immense features, often spanning tens of thousands of light years, and they present astronomers with a classic cosmic whodunit because they have no obvious counterpart in the visible light we see. It's as if we're hearing the faint, powerful echo of a tremendous event that left no other trace for our eyes to find. So what could create such gigantic, invisible structures? The investigation has led scientists down several fascinating paths. One leading hypothesis points to the violent past of galaxy formation itself. These radio loops could be the ancient, fading remnants of a smaller galaxy that NGC 1300 cannibalized billions of years ago. During such a galactic merger, immense tidal forces would have shredded the victim galaxy, stretching its stars and, crucially, its magnetic fields into these vast, arching structures. Over eons, the stars would have dispersed and blended into the larger galaxy, but the magnetic fields, imprinted with high-energy particles, could still be there, faintly glowing in radio light as a fossil record of this long-ago cosmic feast. Another compelling idea points to a more explosive origin. The relentless cycle of star birth and death in a galaxy creates powerful shock waves. When massive stars reach the end of their lives and explode as supernova, they can blow colossal bubbles of hot gas and energetic particles into the surrounding space. These bubbles can rise above the galactic plane and, over time, merge into even larger structures called superbubbles. It's possible that what we're detecting are the radio-emitting shells of these ancient, inflated bubbles, the accumulated size of countless stellar explosions that have occurred over millions of years. Then there's the more exotic possibility. Some researchers have proposed that these radio structures might be a rare and indirect signature of dark matter itself. The prevailing theory suggests dark matter particles, which outweigh normal matter 5 to 1, could occasionally annihilate upon collision with each other. This annihilation would produce a burst of standard particles, including electrons and positrons, that would then interact with galactic magnetic fields to produce synchrotron radiation, the very type of emission we see in these radio loops. If this were true, these faint arcs would be our first direct glimpse at the distribution and behavior of the universe's most elusive substance, a shadowy outline of the dark matter skeleton that holds the entire galaxy together. Radio telescopes like the Very Large Array in New Mexico and the Future Square Kilometer Array are crucial detectives in this case. By meticulously mapping the intensity and polarization of this radio light, astronomers can trace the magnetic field lines within these loops, looking for the distinctive signatures that might point to one origin story over another. The answer remains elusive, making every new observation a potential key to unlocking a secret that is written not in starlight, but in the faint, persistent whisper of radio waves from the distant cosmos. This peculiar silence and the ghostly radio whispers are just the beginning of the deeper strangeness lurking within NGC 1300. To uncover its next great mystery, we must turn to a technique that allows astronomers to literally see the invisible gravitational lensing. This phenomenon, a key prediction of Einstein's theory of general relativity, occurs when the immense gravity of a massive object like a galaxy cluster warps the very fabric of space-time around it. This warping acts like a cosmic lens, bending and magnifying the light from even more distant galaxies behind it. By carefully studying this distorted light, scientists can map the mass of the foreground object, including the vast, unseen halos of dark matter that are thought to surround every galaxy. When researchers applied this powerful technique to NGC 1300, they expected to find a relatively smooth and symmetrical halo of dark matter enveloping the galaxy, a spherical distribution that neatly aligned with our most trusted cosmological models. What they found instead was deeply puzzling. The dark matter halo appears to be oddly lopsided, uneven, and clumpy. It's as if this invisible skeleton, which should provide a uniform gravitational scaffold for the entire galaxy, is instead lumpy and asymmetrical, defying the clean, predictable structure that theory demands. This discovery sends ripples through our fundamental understanding of both dark matter and galaxy formation. For decades, the prevailing cold dark matter model has been exceptionally successful at explaining the large-scale structure of the universe. This model posits that dark matter particles are cold, meaning they move relatively slowly, allowing them to clump together easily under gravity to form smooth, massive halos. The apparent lumpiness and asymmetry around NGC 1300 challenges this very notion. It suggests that dark matter might not be as simple or as cold as we've assumed. Perhaps these particles possess properties we haven't yet accounted for. Maybe they interact with each other through some unknown force, or perhaps they are warmer and faster moving, which would prevent them from forming the perfectly smooth halos our simulations predict. To understand the implications, astronomers run incredibly complex computer simulations, creating digital universes where they can tweak the rules of physics. When they input the standard properties of cold dark matter, their virtual galaxies consistently develop those smooth, spherical halos. But when they try to replicate the clumpy, lopsided halo observed around NGC 1300, the models struggle. They have to introduce new variables, perhaps stronger self-interactions between dark matter particles that cause them to scatter and create uneven distributions, or maybe the lingering gravitational effects of an ancient, unseen collision with another galaxy that stirred up the dark matter like a spoon in a cup of coffee, creating ripples and clumps that have yet to settle. The stakes of solving this mystery could not be higher. Dark matter is the unseen architect of the cosmos, the hidden framework upon which all visible structures are built. If its fundamental properties are different than we've believed, it forces us to rewrite the story of how galaxies like our own Milky Way came to be. It challenges the entire timeline of cosmic evolution. The strange, lumpy halo of NGC 1300 is more than just an anomaly. It's a potential window into the true nature of the majority of matter in the universe, a cryptic clue that we are only just beginning to decipher. Moving out from the galaxy's enigmatic core and invisible halo, we arrive at its most prominent and stunning feature, the magnificent central bar. This colossal structure, a dense lane of stars, gas, and dust stretching tens of thousands of light-years, acts as a primary cosmic highway, funneling material inward toward the hungry black hole. But as astronomers trained their most sensitive instruments on this bar, they discovered it holds a secret of its own, a volatile and contradictory personality that defies our expectations of how stars are born. Rather than displaying a uniform or predictable rate of creation, The bar is a patchwork of extreme activity and profound silence, with furious stellar nurseries blazing right next to vast, dormant deserts of gas. It's a scene of cosmic schizophrenia, and understanding its triggers is paramount to decoding the life of this galaxy. This erratic star formation presents a classic cosmic puzzle. Why would one dense cloud of gas collapse under its own gravity to ignite a million new suns, while an apparently identical cloud right next to it remains still and dark for eons? The answer isn't straightforward, and it forces us to look beyond simple density and consider the intricate physics governing these environments. One of the primary suspects is the very flow of gas along the bar itself. Think of the bar not as a static structure, but as a dynamic, rotating river of material. As this river flows, it can create regions of intense pressure and turbulence, cosmic traffic jams where gas clouds collide, compress, and ultimately trigger a chain reaction of star birth. Meanwhile, other sections of the river might be flowing too smoothly or too rapidly, preventing the gas from clumping together effectively, leaving those areas quiet and inactive. Another powerful influence could be the galaxy's magnetic field, an invisible force that weaves through the bar like a complex spiderweb. These fields are incredibly strong, and they can act like cosmic scaffolding, providing support to vast clouds of gas that would otherwise collapse to form stars. In regions where the magnetic field is particularly orderly and robust, it can effectively resist the pull of gravity, putting star formation on hold. However, if something disrupts that magnetic scaffolding, perhaps the shockwave from a nearby supernova or a collision between gas clouds, the support can vanish in an instant, allowing gravity to win and triggering a sudden, violent burst of stellar birth. This delicate balance between magnetic support and gravitational collapse could be the key to the bar's patchy appearance. We cannot ignore the potential for external influences either. While NGC 1300 appears isolated, it's possible that a close encounter with a small, undetected dwarf galaxy or a subtle gravitational nudge from a passing structure in intergalactic space could have sent ripples through the bar. These ripples would travel through the gas, compressing it in some areas and rarefying it in others, creating a perfect and highly localized recipe for the sporadic star formation patterns we observe. The evidence for such an event might be faint, but it remains a compelling explanation for such an uneven distribution of activity. The tools that reveal this story are as advanced as the mystery itself. Optical telescopes show us the brilliant blue light of young, hot stars, but they can't peer through the bar's thick dust lanes. This is where the infrared and ultraviolet eyes of observatories like the Spitzer Space Telescope and the Hubble Space Telescope become indispensable. Infrared light penetrates the dust, revealing the hidden heat signature of nascent stars still swaddled in their dusty cocoons. Ultraviolet light, on the other hand, is emitted brilliantly by the most massive and short-lived stars, pinpointing the very newest stellar nurseries that have just switched on. By combining these views, astronomers create a complete timeline of star formation, uncovering not just where it's happening now, but where it was happening recently and where it might erupt next. This bizarre behavior in NGC 1300's bar forces a re-evaluation of these common galactic structures. We once viewed bars as simple, efficient mechanisms for feeding a central black hole. Now we see they are also incredibly complex regulators of a galaxy's lifeblood, capable of both nurturing and stifling new solar systems in a seemingly capricious manner. The pattern of star formation within this bar is a dynamic record of the physical processes at work, a record of flows, fields, and possibly ancient interactions. Deciphering it doesn't just explain one galaxy's quirks, it helps us understand the fundamental and often chaotic conditions that give rise to stars everywhere, including the one that gives life to our own world. Leaving the chaotic stellar nurseries of the central bar, our investigation takes a turn toward the seemingly empty spaces between the stars, where another profound mystery is hurtling through the void. Astronomers have detected enormous clouds of pure hydrogen gas streaking through the outer reaches of NGC 1300 at velocities so immense they defy logic. These aren't just fast-moving objects, they are cosmic projectiles traveling at speeds that should be impossible for any structure still considered part of the galaxy. According to our fundamental understanding of gravity, anything moving this fast should have achieved escape velocity long ago, breaking free from the galaxy's gravitational pull and sailing off into intergalactic space. The fact that we observe them still within the galactic environment means one of two things. Either our calculations of the galaxy's total mass are drastically wrong, or these clouds are being propelled by a force we have yet to identify, making them celestial speedsters on a journey with no clear origin or destination. To unravel this puzzle, scientists have turned to the precise art of spectroscopy, dissecting the light from these clouds to understand their composition and motion. The resulting data visualizations are not just colorful graphs, they are vital clues in a cosmic detective story. Each spectrum shows the distinctive fingerprint of hydrogen gas, but this fingerprint is dramatically shifted. This Doppler shift, the same effect that makes a siren's pitch change as it races past you, tells us exactly how fast these clouds are moving relative to us. When visualized, the data reveals stark, pronounced peaks that are stretched far from their expected positions on the spectrum, a clear and quantitative measure of their astonishing velocity. These visualizations make the abstract concept of speed terrifyingly real, providing the hard evidence that these clouds are in a category of their own, moving under rules we don't yet fully comprehend. So where did these intergalactic sprinters come from? Researchers are pursuing several compelling origin stories, each with dramatic implications. One leading theory suggests these clouds are the cosmic debris from a violent encounter in the galaxy's ancient past. If NGC 1300 collided with and absorbed a smaller dwarf galaxy billions of years ago, the immense tidal forces of the collision would have ripped stars and gas from the victim, flinging this material outward at incredible speeds. While most of the stellar debris would have long since settled or been consumed, these tenuous clouds of pure hydrogen, being far less affected by friction and gravitational drag, could still be racing along their original high-velocity trajectories, acting as permanent fossils of a long-forgotten galactic merger. A second, more explosive hypothesis points the finger directly at the galaxy's quiet heart. Despite its apparent dormancy, the central supermassive black hole might have had periods of intense activity in the relatively recent past. During these active phases, it could have generated powerful jets of energy and matter, shooting out from its poles at nearly the speed of light. These jets would have acted like cosmic blowtorches, plowing into surrounding clouds of gas and accelerating them to these tremendous observed velocities. In this scenario, the high-speed clouds we see today would be the lingering shock waves from these ancient eruptions, a testament to a time when the galaxy's core was anything but silent. A third possibility is perhaps the most intriguing. These clouds might not be native to NGC 1300 at all. They could be lone wanderers, primordial clouds of hydrogen that have drifted through the vast emptiness of intergalactic space since the dawn of the universe. As they journeyed, they might have passed too close to the galaxy and are now in the process of being captured by its gravity. Their high speed wouldn't be from propulsion, but from their initial trajectory as they fall into the galaxy's gravitational well for the very first time. We would be witnessing the rare and ongoing process of a galaxy gathering new raw material from the void, a slow motion capture that will eventually provide fuel for future generations of stars. Determining which of these stories is correct requires looking for subtle chemical clues within the clouds themselves. If the clouds are tidal debris from a devoured dwarf galaxy, their metallicity, the abundance of elements heavier than hydrogen and helium, should be very low, as small galaxies often have less enriched gas. If they are outflows from the galactic center, they might carry a specific chemical signature or show evidence of being heated to extremely high temperatures, And if they are pristine intergalactic gas, they should be almost purely hydrogen and helium, virtually untouched by the stellar furnaces that create heavier elements. Each observation narrows the possibilities, bringing us closer to understanding not just the history of these peculiar clouds, but the dynamic and often violent processes that continue to shape galaxies across cosmic time. As we shift our gaze from the high-speed hydrogen clouds to the very fabric of the galaxy, we encounter a mystery that is literally hiding in plain sight, or more accurately, hiding in the dust. Scattered throughout the spiral arms and central bar of NGC 1300 are enigmatic, point-like sources of intense infrared radiation. These are not the brilliant beacons of visible starlight we're accustomed to seeing. They are cryptic objects glowing with the heat of hidden processes, and they have become one of the most compelling puzzles for modern observatories. When astronomers first mapped the galaxy in infrared light using the Spitzer space telescope, they expected to see the diffuse warmth of vast dust clouds. Instead, they pinpointed these incredibly bright, compact sources, cosmic hotspots that have no obvious counterpart in optical images. It's as if the galaxy is studded with invisible diamonds, each radiating a powerful thermal signature while remaining completely shrouded from our normal view. The investigation into these unidentified infrared sources is a perfect example of astronomical detective work, requiring a multi-wavelength approach to piece together their identities. The initial clues came from Spitzer's instruments, which revealed these objects to be extremely hot and remarkably small. This immediately ruled out large-scale structures like nebulas. The next major breakthrough arrived with the unparalleled power of the James Webb Space Telescope, or JWST. Its incredible resolution and sensitivity in the infrared spectrum allowed scientists to peer deeper into these points of light than ever before, dissecting their emissions with stunning precision. The data from Webb didn't just provide better pictures, it delivered detailed spectroscopic fingerprints, revealing the chemical composition and physical conditions within each source, turning anonymous blips into a catalog of specific, yet still mysterious, candidates. So what could these hidden powerhouses be? One of the leading theories points to massively embedded star clusters. Imagine a stellar nursery so dense and shrouded in its own cosmic cocoon of gas and dust that the brilliant light of hundreds of thousands of newborn stars is almost completely trapped. The visible light is absorbed by the surrounding material, but that energy doesn't just vanish, it's converted into heat. The entire colossal structure then radiates this energy as a tremendous outpouring of infrared light, appearing to us as a single, incredibly bright point source. JWST data has begun to find hints of complex molecules and ices in the spectra of some sources, which strongly supports this idea of deeply embedded regions where star formation is occurring on a truly monumental scale. A second, more violent possibility is that we are witnessing the final moments of massive stars in a way we rarely get to see: dust-shrouded supernova. In a typical supernova, a star explodes and creates an intensely bright flash of visible light that can outshine an entire galaxy. But if that explosion were to occur in an exceptionally dense region of dust, the visible light would be immediately swallowed up. The surrounding dust would absorb that catastrophic energy, heat up to extreme temperatures, and glow brilliantly in the infrared for years or even decades after the initial event. What we might be detecting are the long-lasting, warm afterglows of these hidden stellar deaths, cosmic tragedies whose full spectacle was entirely concealed from our view. Perhaps the most exotic theory suggests these point sources could be evidence of a long-sought class of black holes, the intermediate mass black holes. Astronomers are confident that stellar mass black holes form from collapsing stars and that supermassive black holes reside in galactic centers, but the middle ground black holes weighing between 100 and 100,000 times the mass of our Sun has been incredibly elusive. An object of this mass actively feeding on gas and dust within a dense cloud would generate immense friction and heat, producing a fierce infrared glow while remaining completely obscured at other wavelengths. The gravitational influence of such an object could also explain any unusual motions observed in the surrounding gas, making it a prime candidate for some of these unidentified infrared emitters. The implications of solving this mystery are vast. If these are indeed embedded star clusters, they represent a mode of star formation far more extreme and efficient than we see in our own galaxy, which would force us to revise our models of how galactic environments influence the birth of stars. If they are hidden supernova, they suggest that our census of these cataclysmic events is incomplete, meaning we have been underestimating the true rate at which stars are dying in certain types of galaxies. And if even one of these sources is confirmed to be an intermediate mass black hole, it would provide the crucial missing link in our understanding of how the supermassive giants at the centers of galaxies grew to such immense sizes over the history of the universe. Each of these tiny, bright points in the infrared data is a potential key to unlocking a much larger cosmic story. Yet another layer of intrigue reveals itself when we examine the grand design of the galaxy itself. From a distance, the spiral arms of NGC 1300 present a near-perfect picture of cosmic symmetry, two majestic arcs swirling outward from the ends of the central bar in a beautiful, balanced dance. It's the kind of flawless structure that makes for a stunning poster on an astronomer's wall. But when scientists analyze this grandeur with the cold, precise eye of photometric instruments, that perfect symmetry shatters. The arms are not identical twins, they are siblings with distinct differences. One arm appears slightly brighter, more densely packed with young, blue stars and glowing nebulae, while its counterpart is comparatively dimmer and perhaps less organized. In an isolated, undisturbed galaxy like this one, such a pronounced asymmetry is deeply unexpected. It's a crack in the cosmic facade, a subtle imperfection that hints at a dynamic and possibly turbulent history. This symmetry breaking presents a fascinating puzzle because the prevailing theory of spiral structure, known as the density wave theory, suggests these arms should be remarkably uniform. This theory proposes that the arms are not fixed structures made of the same stars, but are instead like traffic jams moving through a stream of stars and gas. As material enters the wave, it compresses, triggering star formation and lighting up the arm. It then exits the other side, leaving the bright arm behind. In a stable, isolated system, this process should create arms of nearly equal brightness and structure. The clear asymmetry in NGC 1300 indicates that something has recently disturbed this delicate equilibrium, throwing the galaxy's graceful rhythm slightly out of sync. So what could cause one arm to shine brighter than the other? Astronomers are investigating several compelling triggers. The most dramatic possibility is a minor galactic merger. While NGC 1300 appears alone now, it may have recently cannibalized a very small dwarf galaxy or a massive globular cluster. The gravitational wake from this event would have rippled through the galactic disk like a stone thrown into a pond. These ripples could have compressed the gas in one spiral arm more efficiently than the other, leading to a sudden, localized burst of star formation that makes that arm blaze with the light of millions of new stars. The evidence for this ancient feast would be faint, perhaps in the form of a faint stream of stars or a slight warp in the outer disk, but the enhanced stellar activity in one arm could be its lasting legacy. Another explanation looks inward to the galaxy's own dynamic heart. The central bar itself is not a rigid, static structure. It rotates and it can experience its own instabilities. It's possible that a slight asymmetry in the bar's own mass distribution or rotation could be transferring more gas and dust into one spiral arm than the other. This would effectively give one arm more fuel for star formation, making it the brighter, more active sibling. This internal cause would mean the galaxy is creating its own imbalance, a self-induced lopsidedness driven by the complex choreography of its billions of stars. To put this in perspective, we can look at other galaxies. Compare a Hubble image of the perfectly symmetrical Whirlpool galaxy with its partner to an image of NGC 1300. The difference is striking. The Whirlpool's arms are being tidally stretched and triggered by its interacting companion, creating a clear and expected asymmetry. NGC 1300 has no such partner, making its imbalance far more mysterious. This comparative analysis is crucial. It rules out the obvious external cause and forces us to consider more subtle and intriguing possibilities. The solution to this puzzle lies in meticulously mapping the ages of the stars within each arm. If the brighter arm is filled with stars that are all roughly the same young age, it points to a single, recent triggering event like a merger. If the star-forming regions are of varying ages, it suggests a more persistent, internal driver is at work, constantly feeding that arm with more material. This subtle flaw in the galaxy's beautiful design is a window into its recent past and the dynamic forces that continue to shape its evolution. Yet another layer of the galaxy's mystery reveals itself not in visible light or radio waves, but in the high-energy realm of X-rays, where the galaxy's quiet heart occasionally and without warning erupts. Deep within the core of NGC 1300, orbiting observatories have detected something deeply puzzling. Brief, intense, and periodic bursts of X-ray radiation that flare up from the nucleus with the power of millions of suns before just as suddenly fading back into silence. These aren't the steady, predictable signatures of a consistently feeding black hole. They are violent, short-lived tantrums, cosmic hiccups of immense energy that arrive on a rough schedule we are only beginning to trace, and they point to a dramatic process unfolding in the extreme environment around the supermassive black hole that our current models struggle to explain. To understand the sheer strangeness of these events, we need to look at the data. Specialized telescopes like NASA's Chandra X-ray Observatory and the European Space Agency's XMM Newton don't see pictures in the way Hubble does. They capture photons of high-energy light and translate them into light curves, graphs that plot brightness against time. The light curve for one of these bursts is unmistakable. It shows a flat, quiet line representing the black hole's typical dormancy, which then suddenly spikes upward in a near-vertical line, reaching a peak of incredible intensity in a matter of hours. This peak holds for a short while before the line plummets back down, often taking days or weeks to return to its original baseline. This sharp, rapid rise and slow decline creates a distinct, skewed peak on the graph, a fingerprint that is very different from the light curves of other known high-energy events, marking it as something unique and unexplained. So what could possibly cause these violent yet periodic energy outbursts? Astronomers are actively debating several compelling theories, each with dramatic implications. The leading hypothesis involves the black hole's irregular diet. We already know the central black hole is unusually quiet, but it might not be fasting entirely. It could be feeding on a clumpy, inconsistent stream of material. Imagine a vast cloud of gas or a small star on a long, elliptical orbit that brings it dangerously close to the black hole on a regular cycle. Each time it swings by, the black hole's immense gravity strips away layers of material. This matter doesn't fall in smoothly. It clumps and sputters as it spirals inward, heating up to millions of degrees in the process and releasing a tremendous burst of X-rays just before it vanishes across the event horizon. The periodicity of the flares could then be a direct clock, ticking off the orbital period of this doomed object as it makes its repeated close passes. A second, more catastrophic idea is that we are witnessing the drawn-out death of a single star. In what's known as a partial tidal disruption event, a star ventures too close to the black hole but isn't completely destroyed. Instead of being ripped apart in one go, the black hole's gravity strips material from the star's outer layers each time it passes perihelion, its point of closest approach. The star survives the encounter but is diminished, destined to loop around on a long orbit only to have another piece of itself torn away on its next pass. Each of these stripping events would unleash a fresh surge of X-rays as the stellar material is consumed. This grim scenario could produce a series of flares spaced months or even years apart, a periodic reminder of the star's ongoing dismemberment. Perhaps the most exciting possibility is that these bursts are evidence of a completely new type of high-energy astrophysical event, one that hasn't yet been described in our textbooks. The unique structure of the barred spiral galaxy might be creating conditions unlike anything we've seen elsewhere. The complex interplay of magnetic fields within the bar could be periodically reconnecting, snapping like overstretched rubber bands and releasing enormous amounts of stored energy directly into the nucleus. Or we could be seeing the effects of a previously unknown instability within the black hole's accretion disk itself, a kind of gravitational resonance that builds up pressure until it explodes outward in a regular pulse of high-energy radiation, a heartbeat echoing from the edge of space-time itself. The quest to pinpoint the true cause is a race against time and technology. Astronomers are now engaged in long-term monitoring campaigns, using multiple observatories to watch the nucleus of NGC 1300 across the electromagnetic spectrum simultaneously. The goal is to catch one of these flares in the act and see what else happens. If a flare is accompanied by a sudden brightening in ultraviolet or optical light, it would strongly support the tidal disruption idea as the stellar debris becomes violently heated. If the flare is purely in X-rays with no counterpart at other wavelengths, it might point to a more exotic magnetic or disk instability event. Each new observation adds a crucial piece to the puzzle, bringing us closer to understanding the violent and cyclical processes that can awaken even the quietest of cosmic giants. But perhaps the most profound mystery surrounding these magnetic fields is the question of their origin. How did such a powerful and organized structure come to be? One school of thought suggests an internal, self-perpetuating process known as a dynamo. As the galaxy rotates, the motion of its conductive plasma, the ionized gas between the stars, could act like a gigantic electrical generator, stretching and twisting weak, primordial magnetic fields and amplifying them over billions of years into the powerful structures we observe today. The rotation of the bar itself could be the engine driving this process, systematically winding the magnetic field lines tighter and tighter, much like spinning a rope to make it taut. An alternative and equally fascinating theory points to an external and violent birth. Galactic magnetic fields might be seeded by events on a truly colossal scale. When the first stars and galaxies formed, their eventual deaths in supernova explosions would have flooded space with not just heavy elements, but also with powerful magnetic fields. If NGC 1300 formed from a cloud of gas that was already magnetized by these ancient events, its field would have been inherited and then further concentrated and organized by its subsequent evolution. It's even possible that a past merger with another galaxy injected a fresh, powerful magnetic field into the mix, which was then captured and shaped by NGC 1300's dominant rotation. The true answer likely lies in a combination of these processes, a complex history of inheritance, dynamo action, and structural shaping that has created a magnetic architecture unique to this cosmic island. And just when we think we've mapped the outermost edges of NGC 1300, our radio telescopes reveal its final, most ghostly secret. Stretching far beyond the bright disk of stars, far past the faint halo of ancient suns, are immense, wispy filaments of cold, neutral hydrogen gas. These are not the high-speed clouds we encountered earlier. These are vast, faint, and relatively slow-moving structures that trace delicate arcs and tendrils into the near-total emptiness of intergalactic space. They form a cosmic fingerprint, an ethereal signature of events that occurred billions of years ago, and their very existence forces us to rewrite the story of where galaxies like this one get their raw material and how they have grown over cosmic time. To understand why these filaments are so revolutionary, we need to appreciate what a typical, undisturbed spiral galaxy is supposed to look like. Our standard models predict a relatively clean edge. The visible disk of stars should transition smoothly into a more diffuse stellar halo, and beyond that, there should be mostly nothing, the dark, empty void between galaxies. The discovery that NGC 1300 is surrounded by this complex web of primordial gas is like finding the overgrown, crumbling foundation of an ancient castle far beyond its standing walls. It tells us that the galaxy's true extent is much larger than what we see with our eyes, and its history is far more active and messy than its current, isolated appearance suggests. So where did this enormous reservoir of extragalactic gas come from? Astronomers are piecing together the evidence, and it points to two dramatic opposing narratives. The first is a story of loss and destruction. These filaments could be the fading tidal tales from an ancient encounter. If a small dwarf galaxy ventured too close to NGC 1300 in the distant past, the larger galaxy's immense gravity would have shredded it, pulling it apart into long, streaming arcs of stars and gas. Over billions of years, the stars in these streams would have slowly dispersed or been absorbed, but the lightweight hydrogen gas, less affected by gravity, would remain, lingering as these faint, filamentary ghosts, the last visible remains of a galaxy that was completely consumed. The second narrative is one of growth and construction. Instead of being debris from a destruction, these filaments could be the opposite, a construction site, the scaffolding for the galaxy's future. This hydrogen could be pristine, unprocessed gas falling into the galaxy for the very first time from the vast cosmic web. This web is the theoretical, spider-like network of dark matter that connects the universe, and along its strands, primordial gas from the Big Bang is thought to flow steadily into galaxies, providing the fresh fuel needed to form new generations of stars. In this scenario, we are catching NGC 1300 in the act of a slow-motion feast, gradually drawing in this raw material from the intergalactic medium to sustain its star-forming machinery for eons to come. Distinguishing between these two histories, a tale of carnage or a story of accretion, requires incredibly sensitive observations. Radio telescopes like the Green Bank Telescope and the Future Square Kilometer Array are tasked with this delicate work. By mapping the precise velocity and density of the gas in these filaments, astronomers can trace their motion. Are the filaments flowing away from the galaxy, as would be expected from tidal debris flung outward, or are they flowing inward as predicted by the cosmic web accretion model? The initial data suggests a complex picture, possibly even a combination of both processes, indicating a history rich with both violent interactions and quiet, steady growth. The implications of these ghostly structures reach far beyond a single galaxy. If this pristine gas is indeed falling in, it represents a primary way galaxies acquire the fuel to keep making stars. This challenges the old idea that galaxies form all their stars early on and then slowly wind down. Instead, it supports a more dynamic model where galaxies are living, breathing entities, constantly replenishing their stores from the cosmos around them. Furthermore, the chemical composition of this gas is a time capsule. If it is truly primordial, it should contain almost no elements heavier than hydrogen and helium, having never been fused in the heart of a star. Confirming this would give us a direct sample of the universe's original matter, untouched and unaltered for over 13 billion years. These faint whispers of hydrogen are therefore more than just a curious phenomenon. They are a direct link to the galaxy's violent past and its potential for future growth, a reminder that even in the darkest voids, the story of a galaxy is still being written. This peculiar pattern of star formation leads us to our next great mystery, one that is written not in the galaxy's grand structures, but in the very nature of its stellar citizens. As astronomers performed a detailed census of the stars within specific regions of NGC 1300, they uncovered a startling demographic anomaly. In several distinct pockets, particularly along the inner edges of the spiral arms and within sections of the central bar, they found populations of stars that were almost perfect contemporaries. These stars weren't just vaguely similar in age, they were born within a remarkably narrow window of cosmic time, a period so brief in astronomical terms that it points to a single, explosive, and synchronized burst of star formation. It's as if a celestial conductor gave a sudden downbeat and millions of suns ignited in near-perfect unison, a phenomenon that challenges our core understanding of how stars are typically born in a slow, gradual, and ongoing process. This discovery of co-natal stars, stars born together in a sudden rush, forces a significant rethink. The prevailing model of star formation in galaxies like our own Milky Way is a continuous, almost stately affair. It's a slow dance where individual, isolated gas clouds gradually collapse over millions of years, leading to a steady trickle of new stars with a wide range of ages in any given neighborhood. Finding entire communities of stars that are all the same age shatters this picture. It suggests that something powerful and specific must have swept through these regions, acting as a universal trigger that pushed vast and separate reservoirs of gas over the edge into collapse all at once. This isn't just a local event, it's evidence of a galaxy-wide coordinating mechanism. So what could provide such a powerful, synchronizing push? One of the most compelling suspects is a large-scale shock wave rippling through the galactic disk. The source of such a shock could be spectacularly violent. Imagine the death of 100 massive stars in a relatively short period, a coordinated series of supernova explosions in a nearby cluster. The cumulative effect of their blast waves would be like a single titanic shock front plowing through the interstellar medium, compressing every cloud of gas it encounters and initiating a wave of star formation in its wake. Alternatively, the shock could have an external origin. If a sizable cloud of intergalactic gas, perhaps the remnant of a devoured dwarf galaxy, were to come raining down onto the disk of NGC 1300, the impact would create a tremendous ripple effect, a pressure wave that could trigger starbirth across an entire sector of the galaxy simultaneously. Another potential trigger is a phenomenon known as feedback, a process where the galaxy essentially regulates itself. The powerful stellar winds from a previous generation of massive stars, or the intense radiation pressure they emit, can actually sweep up surrounding gas into dense, massive shells. These shells can become gravitationally unstable and then fragment, collapsing not into individual stars but into entire clusters of them at once. In this scenario, one generation of stars literally creates the conditions for the next generation to be born together in a single, punctuated event. The bar of NGC 1300 itself could be the ultimate facilitator. As it rotates, it might funnel gas into a specific region until a critical density is reached, causing a sudden, widespread collapse, a stellar baby boom on a galactic scale. To solve this puzzle, astronomers turn to the science of stellar archaeology. By analyzing the light from these stellar populations with powerful spectrographs, they can determine not just their age, but also their metallicity, the abundance of elements heavier than hydrogen and helium. If all the stars in a group have not only the same age but also an identical and unique chemical fingerprint, it's the smoking gun. It proves they all formed from the same specific reservoir of gas, a cloud that was chemically homogenized by a previous event before it was triggered to collapse. This precise forensic data allows scientists to rule out some theories and support others, gradually piecing together the history of the violent, coordinating events that can make a galaxy light up with new suns in a spectacular, synchronized flash. This demographic puzzle of synchronized stellar births leads us to a mystery of a different kind, one that concerns not the stars themselves, but the ancient, glittering cities they call home. Scattered throughout the halos of most large galaxies, including our own Milky Way, are dense, spherical swarms of stars known as globular clusters. These are among the oldest structures in the universe, each containing hundreds of thousands of stars bound together by gravity in a space just a few dozen light-years across. They are the galactic elders, relics from the universe's fiery youth, and their numbers tell a story about a galaxy's history. For a grand barred spiral like NGC 1300, with its immense mass and classic structure, astronomers expected to find a large entourage of these ancient clusters orbiting it like a royal guard. But when they went to count them, the numbers simply didn't add up. The galaxy is missing a significant portion of its expected globular clusters, and their absence creates a conspicuous hole in our understanding of how such galaxies assemble over time. To grasp just how unusual this is, we can look to our own cosmic neighborhood. The Milky Way, a smaller spiral galaxy, is known to host at least 150 of these ancient clusters. Larger galaxies, especially those sitting at the centers of galaxy groups, can have many thousands. NGC 1300, a majestic isolated spiral, falls into a mass category where models predict it should possess several hundred. Yet detailed surveys, particularly those conducted by the Hubble Space Telescope to peer into the galaxy's halo, have consistently come up short. The predicted population isn't there. It's not that the clusters are too faint to see, it's that they genuinely seem to be missing. This deficit forces astronomers to ask a difficult three-part question. Were these clusters destroyed? Did they never form in the first place, or are they somehow hiding from us in plain sight? One compelling theory is a history of galactic violence. Globular clusters are notoriously tough, but they are not indestructible. If NGC 1300 had a more chaotic past than its current serene appearance suggests, perhaps undergoing a major merger billions of years ago, the immense gravitational tides from that collision could have ripped apart countless clusters. The process is called tidal disruption. As clusters repeatedly pass through the dense galactic plane or swing too close to the massive core, gravitational shear can pull them apart, stretching them into long streams of stars that eventually dissolve into the general halo. The evidence for this ancient carnage would be subtle: faint stellar streams or an overabundance of lone stars in the halo that could be the shredded remains of these once glorious clusters. A second, more radical idea is that the clusters never formed in large numbers to begin with. The formation of globular clusters is thought to be tied to the extreme conditions in the early universe during periods of frenzied star formation. Perhaps the primordial cloud that gave birth to NGC 1300 was different. Maybe it lacked the necessary density peaks or the rapid pressure fluctuations that are required to trigger the birth of these incredibly dense stellar cities. If the raw ingredients or the early conditions weren't just right, the galaxy could have emerged from its formative years naturally deficient in clusters, destined to forever have a quieter halo than its siblings. Then there is the possibility that we are simply looking for them the wrong way. What if the missing clusters aren't missing at all, but are instead hiding within the galaxy's brilliant disk? Some clusters could have migrated inward over billions of years, becoming lost in the glare of the crowded central bar and bulge. Or perhaps a population of clusters formed that is inherently different from what we know. Clusters that are richer in dark matter or that have a different stellar makeup, making them appear fainter and blending in with the background star field. They could be right in front of our telescopes, disguised as something else entirely. Resolving this mystery requires more than just counting points of light. It demands a forensic analysis of the galaxy's history. By studying the precise motions and chemical compositions of the stars in the halo, astronomers can search for the chemical fingerprints of disrupted clusters. They can also look to other galaxies for clues. When we compare NGC 1300 to a similar galaxy like NGC 1512, which has a rich expected population of globular clusters, the difference is stark and undeniable. This comparative approach confirms the anomaly is real and not an error in our observations. The case of the missing globular clusters is far from closed. It remains a tantalizing puzzle about the violent past or unique birth of this beautiful spiral, a reminder that even the oldest and most enduring structures in the universe are subject to the forces of cosmic evolution and change. While the grand structures and dynamic events of NGC 1300 capture our attention, some of its most profound mysteries are hidden within the very chemistry of its starlight, requiring us to dissect its essence one photon at a time. When astronomers train powerful spectrographs on the galaxy's brilliant H2 regions, those vast clouds of glowing hydrogen gas that are the nurseries for new stars, they uncover a compositional anomaly that defies expectation. The spectroscopic fingerprints reveal abnormal, puzzling ratios of fundamental elements, particularly an overabundance of oxygen compared to nitrogen in certain regions. This isn't a trivial discrepancy. It's a direct clue that the processes creating and dispersing the elements of life in this galaxy are operating under a different set of rules, pointing to a history of stellar generations unlike anything we see in our own cosmic backyard. To understand how we uncover this chemical secret, we need to appreciate the power of spectroscopy. It's the ultimate cosmic forensic tool. When the intense ultraviolet light from massive newborn stars within an H2 region floods the surrounding cloud of hydrogen gas, it energizes the atoms within it. As these excited atoms calm down, they re-emit light at very specific, precise wavelengths, each element producing its own unique set of spectral lines, a barcode identifying its presence. By capturing this faint light with massive telescopes and splitting it through a spectrograph, astronomers can not only identify which elements are present, but also measure their relative amounts by analyzing the intensity of their specific lines. The strength of an oxygen line compared to a nitrogen line, for instance, gives us a direct readout of their ratio in that cloud of gas. In NGC 1300, that readout is strangely off-kilter. So what could cause this chemical imbalance? The investigation leads us down two fascinating paths, each with dramatic implications. The first possibility is that we are witnessing the aftermath of an unusual population of stars. The elements that enrich a galaxy are forged in the nuclear furnaces of stars and scattered across space when those stars die in supernova explosions. The amount of oxygen produced is heavily dependent on the mass of the star that creates it. The most massive stars produce copious amounts of oxygen. Nitrogen, however, is largely synthesized in intermediate mass stars through different processes. An abnormal oxygen-to-nitrogen ratio suggests a historical deficit of those intermediate mass stars, or perhaps an overabundance of extremely massive stars that lived fast, died young, and flooded their surroundings with oxygen before they could be balanced out by other sources. This points to a primordial initial mass function, the distribution of star sizes at birth, that was skewed differently in NGC 1300's past, a fundamental difference in how this galaxy built its stellar population. The second, and perhaps more thrilling, theory involves the galaxy sampling exotic ingredients from an external source. If NGC 1300 accreted a significant amount of primordial gas from the cosmic web, a gas that had never been processed inside a star and thus contained only the original hydrogen and helium from the Big Bang, this would dilute the interstellar medium. However, this wouldn't directly create an oxygen overabundance. The more compelling external scenario is that it cannibalized a small, ancient dwarf galaxy. Many of these tiny galaxies are known to have uniquely low metallicities and strange chemical compositions themselves, having experienced a very different star-forming history. The injection of this foreign, chemically distinct gas could have thrown the well-mixed recipe of NGC 1300's interstellar medium into chaos, creating pockets with these unusual elemental ratios that have yet to fully homogenize. The significance of this chemical mystery stretches from the cosmic to the terrestrial. The elements we see in imbalance, oxygen and nitrogen, are not just abstract chemicals. They are fundamental building blocks of planets and ultimately life as we know it. An overabundance of oxygen in a stellar nursery could influence the composition of protoplanetary disks forming there, potentially leading to rocky worlds with crusts and atmospheres radically different from our own. By studying this phenomenon, we're not just solving an academic puzzle about nucleosynthesis, we're investigating the very conditions that set the stage for habitability across the cosmos. The strange chemistry of NGC 1300's nebulas is a stark reminder that the recipe for a planet, or even life itself, might not be universal, but could vary dramatically from one island of stars to another. And just as we begin to map the grand chemical patterns across the galaxy, our attention is pulled back to its enigmatic heart, where a new and remarkably subtle mystery plays out on a rapid, flickering timescale. The 14th strange phenomenon in NGC 1300 isn't a colossal explosion or a vast, invisible structure. It's a delicate, rapid stutter in the light emanating from the galaxy's very core. While the central supermassive black hole remains overwhelmingly quiet in X-rays, sensitive observations in optical and ultraviolet light reveal that its placid demeanor is just an illusion. The nucleus is actually flickering, its brightness fluctuating on surprisingly short timescales, sometimes over just days or weeks. This rapid variability is a tiny, high-frequency tremor running through the galaxy's gravitational core, and it suggests that even in its quiescent state, the beast is not completely asleep. It's snacking. This flickering is a powerful clue because of what it implies about the physical scale of the activity. In astronomy, the speed of a change reveals the size of the source causing it. An object cannot significantly vary in brightness faster than the time it takes light to travel across it. Think of it like this. You can't make an entire football stadium flash on and off in a millisecond because the signal to turn the lights on would take time to reach the far end. Similarly, for the galactic nucleus to change its brightness over a matter of days, the source of that light must be extraordinarily compact, on a scale smaller than the distance light travels in that same time. This immediately points the finger directly at processes happening in the innermost regions of the accretion flow, terrifyingly close to the event horizon of the black hole itself. So what tiny, rapid mechanisms could be causing this flickering dance of light? Astronomers are piecing together a picture of a chaotic and inefficient dining experience. One of the strongest theories involves small-scale instabilities within the thin trickle of gas that is managing to reach the black hole. This accretion flow isn't a smooth, orderly river, it's more like a sparse, sputtering drizzle. Within this flow, tiny clumps of gas, perhaps no larger than our solar system, could be chaotically swirling and colliding. As each individual clump is suddenly compressed and heated to extreme temperatures in the intense gravitational field, it would flare up brightly in UV and optical light for a short period before vanishing over the horizon, creating a single, brief spike in the overall brightness. The combined effect of countless such microflares would be the observed flickering, a visual representation of the black hole's uneven and clumpy diet. Another compelling idea focuses on the accretion disk itself, or what remains of it. In a quiescent state, the disk might be not just thin, but also subject to magnetic turmoil. The powerful magnetic fields threading through the ionized gas can become twisted and tangled, storing enormous amounts of energy. When these field lines suddenly snap and reconfigure in a process called magnetic reconnection, the same phenomenon that drives solar flares on our sun, they release that stored energy in a violent burst of radiation. These magnetic explosions happening across a patchy, unstable disk could easily account for the rapid and unpredictable flickering we detect. A storm of tiny cosmic lightning flashes crackling in the darkness just outside the point of no return. The significance of this flickering extends far beyond this single galaxy. For decades, astronomers have broadly categorized galactic nuclei into two neat boxes, active and quiescent. NGC 1300 is forcing us to acknowledge that this binary is a vast oversimplification. there appears to be a whole spectrum of activity between the brilliant beacon of an AGN and the total silence of a dormant black hole. This low-level, flickering state represents a crucial intermediate mode, a feeding regime that is far more common than we ever realized. By studying the pattern and timescale of these tiny variations, we are essentially learning the grammar of how supermassive black holes eat when food is scarce. It reveals that even when a black hole is not consuming enough to power a brilliant beacon, the processes near its event horizon are still incredibly dynamic and complex, governed by the same brutal physics but playing out on a much smaller and more subtle scale. Now we shift our focus from the high-energy flickers at the core to the cold, dark dust clouds that weave through the galaxy's spiral arms, where a thermal mystery is unfolding. This 15th phenomenon concerns the very temperature of these cosmic dust grains, which should be a predictable affair based on their distance from the nearest stars. Yet, detailed thermal infrared maps from observatories like the Spitzer Space Telescope reveal something is profoundly wrong. Isolated clouds are blazing with heat far from any obvious energy source, while other dense regions are inexplicably deeply cold, as if something is either secretly heating them or actively sucking the warmth away. These anomalous temperatures are more than just a date or discrepancy. They are a clear signal that our basic understanding of the interstellar environment within this galaxy is missing a key piece of the puzzle. To visualize this, picture a thermal map of the galaxy. Vast swaths of the spiral arms glow with the expected warm red and orange hues, indicating dust gently heated by the diffuse light of surrounding stars. But then, scattered across this map are brilliant pinpoint spots of intense white-hot emission tiny clouds that are hundreds of degrees hotter than they should be. Elsewhere, the map shows deep, chilling blues and purples, indicating dust that is bitterly cold and seemingly isolated from all stellar warmth. These hot spots and cold spots stand out like thermal sore thumbs, defying the simple rule that a dust cloud's temperature is solely determined by how much starlight it absorbs. So what could be causing this bizarre thermal behavior? For the mysteriously hot clouds, one compelling theory points to concealed stellar factories. The most intense heat could be coming from deeply embedded, massive protostars, stars so young they are still swaddled in thick, opaque cocoons of their own making. Their brilliant visible light is completely trapped, but that immense energy is absorbed by the surrounding dust and irradiated as a powerful infrared glow, making the entire cloud appear as a single, improbably hot point source without a visible cause. Another, more exotic idea involves the decay of radioactive isotopes forged in a recent, hidden supernova. If a star exploded inside a dense cloud, it could have seeded the dust with unstable elements like aluminum-26. As these atoms decay, they release heat, gently and persistently warming the surrounding dust grains from within like tiny radioactive coals. The inexplicably cold clouds present an even tougher riddle. One possibility is that these regions are dominated by a different type of dust altogether. Perhaps the grains there are much larger or have a different chemical composition, changing their ability to absorb starlight. Larger, dirty, ice-mantled grains might be fantastic at radiating heat away but very poor at absorbing it, causing them to stay perpetually frigid. Another fascinating hypothesis involves magnetic fields. If these cold clouds are permeated by an unusually strong and ordered magnetic field, it could be affecting the way dust grains spin and align. This, in turn, might influence how efficiently they transfer their thermal energy to the surrounding hydrogen gas, effectively allowing the dust to cool itself down to temperatures that standard models never predicted. These thermal anomalies are far from an academic curiosity. They force a re-evaluation of the galaxy's energy budget. If hidden sources are heating dust, it means there is more ongoing star formation or recent stellar death than our optical telescopes have revealed. If the dust itself has different properties, it changes our calculations for how easily new stars can form, as cold, rigid clouds resist gravitational collapse. Each mysteriously hot or cold patch on the map is a clue, a thermal fingerprint left by a process we have yet to fully understand, reminding us that even the most frigid, dark corners of a galaxy can hold the keys to its most energetic secrets. These high-velocity winds represent a colossal force of feedback, a self-regulating mechanism that profoundly impacts the entire galaxy's life cycle. When these outflows smash into the surrounding interstellar medium, they don't just push it aside, they create immense shock waves that compress other, quieter clouds of gas. This compression can be the very trigger for a new wave of star formation, a cosmic case of destruction birthing creation. However, if the outflow is too powerful, it can have the opposite effect, violently shredding potential stellar nurseries and blowing the galaxy's future fuel supply out into the halos of intergalactic space, effectively starving the galaxy and quenching star formation for eons. The outflows in NGC 1300 appear to be doing both simultaneously in different regions, acting as both midwife and executioner for entire generations of stars, their opposing roles adding another layer of beautiful complexity to this galaxy's dynamic story. But the dynamic feedback from these stellar winds isn't the only sign of powerful interactions between stars. Some of the most dramatic partnerships are happening on a much smaller, yet infinitely denser scale. As we peer into the crowded stellar neighborhoods of NGC 1300, we find our 17th strange phenomenon, a curious collection of candidate binary star systems that defy conventional expectations. These aren't your typical twin stars gracefully waltzing around a common center of gravity. These are peculiar pairs locked in bizarre, tight orbits with wildly mismatched masses, and their very existence challenges our established models of how such systems form and evolve over cosmic time. The discovery of these odd couples suggests that in the dense environments of this galaxy, stellar relationships can take on extraordinarily strange and violent forms. Detecting these peculiar binaries is a masterclass in indirect astronomical observation. Since we cannot resolve the individual stars in such a distant galaxy, we rely on their subtle effects on the light we receive. For eclipsing binaries where the orbital plane is edge-on from our perspective, we see a characteristic periodic dip in the star system's overall brightness as one star passes in front of the other. The shape and depth of this light curve reveal the relative sizes and temperatures of the two stars. For spectroscopic binaries, we use the Doppler shift. As the stars orbit one another, they alternately move toward and away from us, causing their spectral lines to rhythmically blur and shift. The speed of this shift allows us to calculate their masses and the shape of their orbit. In NGC 1300, these standard methods are revealing systems with parameters that simply don't fit the standard mold, pointing to histories of unusual formation or dramatic intervention. One of the most compelling types of oddities are the candidate black hole or neutron star binaries. Imagine a system where a perfectly normal, sun-like star is locked in a frantic, close orbit with an utterly invisible companion. The visible star whips around at incredible speed, its motion betraying the presence of a gravitational anchor with a mass several times that of our Sun, yet one that emits no light of its own. This is the classic signature of a black hole or neutron star binary. Finding such systems in a barred spiral galaxy like NGC 1300 is crucial because it tells us about the end results of massive star evolution in this unique environment. The number of these systems, their masses, and their orbital characteristics are all vital data points. They act as fossil records, revealing the initial mass distribution of stars that were born here billions of years ago, and the violence of the supernova explosions that created these dense remnants. Perhaps even more puzzling are the systems with extreme mass ratios. These are pairs where one star is dozens of times more massive than its partner, a cosmic pairing of a giant and a dwarf. According to standard models of star formation within a single cloud, binary stars should be born with masses that are relatively similar. finding such lopsided partnerships suggests a much more chaotic and dynamic origin story. It's highly probable that these systems were not born together but were forced into their gravitational marriage by a third party. In the densely packed core of a star cluster, close gravitational encounters can easily disrupt original binaries and forge new, unlikely pairs in a process called dynamical exchange. It's a stellar partner swap on a galactic scale, and the prevalence of these odd systems in NGC 1300 could be a direct indicator of how frequently such chaotic gravitational interactions occur within its clusters. The implications of these strange binary systems stretch far beyond mere celestial curiosity. They are natural laboratories for testing the laws of physics under the most extreme conditions. A binary system containing a neutron star, for instance, provides an exquisite testbed for Einstein's theory of general relativity. The intense gravitational fields can be measured with incredible precision, and the gradual in-spiral of the orbits over time radiates gravitational waves, those ripples in spacetime first predicted a century ago and only recently directly detected. By studying a population of such systems, astronomers can trace the history of gravitational wave events that have likely already occurred within the galaxy, painting a picture of a universe constantly ringing with these cosmic collisions. Each peculiar orbit and every mismatched mass ratio is a clue, a piece of evidence that helps us rewrite the story of stellar life and death in this magnificent and mysterious island of stars. And just when we thought we had mapped the galaxy across every wavelength, from the gentle heat of infrared to the violent flashes of X-rays, our most powerful orbital observatories have detected a signal from NGC 1300 that is perhaps the most energetic and elusive of all, faint, enigmatic whispers of gamma-ray light. These are not the brilliant, unmistakable bursts associated with colliding neutron stars or supernova. They are a persistent, diffuse, and incredibly faint glow that seems to emanate from the galaxy's general direction. Isolating this signal from the blinding background noise of the entire cosmos is a Herculean task, a feat of modern astrophysical detective work. The Fermi Gamma Ray Space Telescope, our primary eye on this high-energy universe, must spend years collecting photons from a single patch of sky, just to build up a statistical case that the few extra gamma rays it's counting are truly coming from NGC 1300 and not from some other source along the same line of sight. This faint, hard-won excess is the heart of the mystery, a potential clue to processes of unimaginable power occurring within or around the galaxy. Pinpointing the origin of these gamma rays is a classic cosmic whodunit, and the list of suspects is filled with both the exotic and the catastrophic. One of the most thrilling possibilities is that we are indirectly detecting the presence of dark matter. According to prevailing theories, dark matter particles, which make up the vast majority of the galaxy's mass, might not be completely invisible. If certain hypothetical particles, like WIMP weakly interacting massive particles, are real, they could occasionally collide and annihilate each other. This annihilation would be a matter-antimatter event of spectacular proportions, converting their mass directly into energy and producing a shower of standard particles, including gamma rays. The specific energy signature of these gamma rays could be the long-sought smoking gun that finally reveals the true identity of the universe's dominant but unseen material. Detecting this signature from a well-structured galaxy like NGC 1300 would be a monumental breakthrough, offering a direct window into the nature of this cosmic ghost. However, astronomers must always rule out the mundane before embracing the extraordinary, and there are plenty of standard astrophysical events that could be masquerading as a dark matter signal. The galaxy is teeming with natural particle accelerators capable of producing gamma rays. For instance, the powerful shock waves from supernova remnants can accelerate protons to nearly the speed of light. When these relativistic protons collide with other atoms in the interstellar medium, They create unstable particles called pions that rapidly decay, emitting gamma rays in the process. Similarly, the intense magnetic fields around pulsars, the rapidly spinning corpses of massive stars, can generate powerful electric fields that also accelerate particles to high energies, producing a steady gamma ray glow. The combined output of thousands of such sources, each too faint to be seen individually, could easily add up to the faint, diffuse signal we detect, a sort of cosmic chorus of high-energy events rather than a single soloist. There's also the ever-present challenge of background contamination. Our line of sight to NGC 1300 is not a clean, empty tunnel. It's cluttered with the faint emission from distant, unresolved blazars active galaxies with jets pointed directly at Earth, and the truly diffuse gamma-ray fog that permeates intergalactic space, the cumulative light of countless events across the universe's history. Disentangling the specific contribution from NGC 1300 from this foreground and background haze is perhaps the greatest technical challenge in this investigation. It requires incredibly sophisticated statistical models and a deep understanding of the entire gamma-ray sky, turning the analysis into a painstaking process of subtraction and isolation. The implications of solving this mystery are profound, stretching across the entire field of physics. If the signal is confirmed to be from dark matter annihilation, it wouldn't just tell us what dark matter is, it would also allow us to map its distribution within the galaxy with unprecedented precision, confirming or refuting the strange, lumpy halo we suspect exists. If the signal is instead from a population of extreme astrophysical sources, it would reveal a previously unseen level of violent activity within the galaxy, suggesting that its serene optical appearance is a beautiful illusion masking a turbulent and energetic interior. Either way, these faint gamma-ray photons, each carrying 1,000,000 times the energy of visible light, are messengers from the most extreme processes in the universe, and decoding their origin is key to understanding the full, powerful story of NGC 1300. But the strange features of NGC 1300 are not confined to its bright inner regions. This galaxy holds one more secret in its outermost fringes, a subtle distortion that challenges our view of it as a perfectly isolated system. As astronomers map the faint light of its most distant stars, they've discovered the 19th profound phenomenon: the galaxy's outer disk is not flat. Instead, it appears distinctly warped and flared, like a vinyl record left too long in the sun. This gentle bending of the entire galactic plane is a telltale sign of a gravitational disturbance, a cosmic wobble that suggests the galaxy's serene, isolated appearance might be a carefully maintained illusion, masking a history of external interactions with forces we cannot directly see. To understand how significant this is, picture a typical spiral galaxy. We expect it to be a flat, rotating disk, with everything from giant stars to tiny dust grains moving in orderly, circular orbits around the center. A warp is a violation of this perfect order. It means that in the outer regions, the orbits are no longer flat. The stars and gas are moving on tilted paths, causing the entire disk to bend upward on one side and downward on the other. This isn't a temporary ripple. For a warp to be visible, it must be a persistent, stable feature, which means something powerful must be continually sustaining it against the galaxy's own gravity, which is constantly trying to pull it back into a flat plane. So what could cause such a large-scale, enduring distortion? Astronomers use sophisticated computer simulations to test various scenarios, and the evidence points to two compelling and equally fascinating culprits. The first is an ongoing gravitational relationship with unseen dark matter. We know the galaxy is embedded in a vast, lumpy halo of this invisible material. If this halo is not perfectly spherical, if it's slightly squashed or triaxial, its gravitational pull would not be uniform. This asymmetrical tug would constantly act on the outer disk, forcing the stars there to orbit in a slightly tilted manner, creating and then sustaining the warp over billions of years. In this model, the warp is not a scar from a past event, but a permanent state of being, a dance dictated by the shape of the invisible dark matter partner that the galaxy is forever locked in step with. The second leading theory is a story of past violence. While NGC 1300 appears alone now, it may have had a close encounter with a smaller dwarf galaxy or a large stream of intergalactic gas in the relatively recent past, recent meaning within the last 1 or 2 billion years. The gravitational wake from this passing object would have rippled through the galactic disk like a ship's wake through water, pulling the outer stars out of their flat orbits and setting the entire disk oscillating. The visible warp we see today would be the lingering vibration from that ancient collision, a slowly fading echo of a dramatic event that occurred long ago. The fact that it hasn't settled yet tells us just how massive and disruptive that encounter must have been. Distinguishing between these two histories, a constant dark matter influence or a single past encounter, is an active area of research. The key lies in studying the precise dynamics of the warp. By measuring the velocities of stars and gas on the uplifted and downturned sides of the disk, astronomers can trace the pattern and speed of the distortion. A warp that is a stable, rigid structure rotating with the galaxy would strongly point to the dark matter halo as the cause. A warp that shows a more complex, twisting pattern, one that processes or changes over time, would be the hallmark of a decaying oscillation from a past interaction. Each new observation brings us closer to answering whether this beautiful distortion is the signature of a constant, invisible companion or the ghost of a long-vanished galactic neighbor. Yet another enigmatic signal emerges not from the realm of light or gravity, but from the silent spaces between, where our radio telescopes have detected a series of highly unusual, intermittent pulses emanating from deep within the spiral arms of NGC 1300. These are not the steady, metronomic beats of a pulsar, the lighthouse-like signals from a spinning neutron star that astronomers have catalogued for decades. Nor do they match the frenzied, storm-like outbursts of a magnetar, a highly magnetic neutron star known for its violent eruptions. Instead, these signals are something else entirely. Brief, powerful bursts of radio energy that appear at irregular intervals, sometimes clustering together in quick succession before falling silent for weeks or even months at a time. Their unpredictable nature and unique frequency structure have made them one of the most head-scratching mysteries in the galaxy, a pattern that defies easy classification and points toward either a completely new class of astrophysical object or a natural process we have yet to understand. Pinpointing the origin of these signals is a masterclass in modern astronomy's most meticulous techniques. When a radio telescope like the Very Large Array or the Future Square Kilometre Array detects one of these fleeting bursts, it's not creating a picture in the traditional sense. The raw data is a complex waterfall plot, a visual representation of how the signal's intensity changes across different radio frequencies over a fraction of a second. For these mysterious pulses, the waterfall plot reveals a distinctive descending pattern. The signal appears first at higher frequencies and then rapidly sweeps downward to lower ones, creating a characteristic curve that is unlike the signature of any known celestial object. This sad trombone effect, as some astronomers have informally called it, is a crucial fingerprint, a clue that the radio waves are being dispersed and delayed by traversing a significant amount of ionized gas on their journey to us, suggesting they originate from deep within the galaxy's interstellar medium. So what natural astrophysical phenomena could possibly create such brilliant, brief, and repeating radio flashes? The investigation has led researchers down several fascinating, evidence-based paths. One of the most compelling theories involves a specific type of stellar remnant. Imagine a neutron star, but one that is extraordinarily dense and possesses a magnetic field of almost unimaginable strength. This object could be in a unique transitional phase, perhaps slowing its rotation after a period of rapid spinning, and this deceleration might be releasing pent-up energy in sporadic, powerful bursts rather than a steady beam. Alternatively, it could be a neutron star with an unusually strong and complex magnetic field structure. As this field periodically reconfigures and snaps, it could unleash these intense radio bursts in a process similar to the magnetic reconnection that causes solar flares on our Sun, but on a vastly more energetic scale. Another natural explanation points to a dramatic binary system. A pair of stars locked in a tight, eccentric orbit could produce periodic signals if one of them is a highly magnetic white dwarf or a neutron star. As they swing close together on their elliptical path, the immense gravitational forces could trigger massive starquakes on the surface of the dense remnant or cause sudden, catastrophic transfers of material, events that would release a tremendous burst of radio energy. The irregular timing of the signals could then be explained by the complex dynamics of this orbital dance and the precession, or wobble, of the star's rotation axis, which would only allow the beam of radio emission to sweep across Earth at unpredictable intervals. While the vast majority of the scientific community is focused on these and other natural explanations, the highly structured and anomalous nature of these signals has inevitably sparked broader speculation. The possibility of a technosignature, a detectable sign of technology developed by an intelligent civilization elsewhere in the galaxy, is a hypothesis that must be considered, however remote. The concept is not that the signal is a deliberate message, but rather that it could be a byproduct of incredibly advanced technology, perhaps the equivalent of a powerful radar system, energy transmission, or propulsion mechanism operating on a scale we can scarcely imagine. This idea is explored not as a likely conclusion, but as a necessary part of the scientific process of eliminating all possibilities, a testament to the truly extraordinary and unexplained characteristics of the phenomenon. The ongoing search for an answer is a global effort, a testament to international scientific collaboration. Every time one of these pulses is detected, an alert instantly shoots out to observatories around the world, triggering a frantic race to turn other telescopes, optical, infrared, X-ray, toward the same point in the sky. The goal is to catch a counterpart, any other flash or emission at a different wavelength that could be linked to the radio burst. A simultaneous X-ray flare would point strongly toward a magnetar or a neutron star event. A faint, flickering optical source could indicate a binary system. To date, no such counterpart has been definitively identified, which only deepens the mystery, suggesting that the source of these pulses might be dark and quiet at all other wavelengths, emitting its powerful signal only in the radio realm before vanishing back into complete obscurity. Each new detection is another piece of a puzzle that is slowly forcing us to expand our understanding of how matter and energy can behave under the most extreme conditions the universe has to offer. But the 21st phenomenon transports us from the fleeting spark of radio pulses to the galaxy's most permanent and dominant feature, its colossal central bar. This immense structure, a rigid backbone of stars and gas stretching across tens of thousands of light years, is the very engine of the galaxy, the primary funnel channeling material inward. Yet when astronomers meticulously measured its mass and length, they uncovered a profound structural enigma. The bar is simply too big for its own good. It is more massive and significantly longer than our best dynamical models of barred spirals allow for a stable, long-lived structure. According to our understanding of galactic physics, a bar of this immense scale should be inherently unstable. It should buckle, warp, or dissolve over time under the immense gravitational stresses of its own weight. The fact that it hasn't, that it persists in a state of seeming perfection, forces a complete re-evaluation of how such colossal features form and endure. To understand why this bar defies expectations, we need to picture a galaxy not as a rigid sculpture, but as a dynamic, fluid system in a constant state of gravitational negotiation. The stars and gas within the bar orbit the galactic center, but they don't do so in simple circles. Their paths are elongated, trapped within the bar's powerful gravitational field, which itself is created by the collective mass of all those same stars. This creates a feedback loop. Computer simulations that model the evolution of these structures show a clear limit. If a bar grows too massive, its own gravity triggers instabilities. It can thicken vertically into a peanut-shaped bulge, or it can begin to wobble and eventually break apart, transferring its angular momentum to the galaxy's halo and disk. The bar in NGC 1300 has clearly crossed this theoretical stability threshold, yet it remains remarkably thin, flat, and coherent. It's a cosmic contradiction, a structure that by all rights shouldn't exist in its current form, and its very presence is a direct challenge to our simulations. This puzzle has led astrophysicists to propose several compelling theories for its formation and endurance. One fascinating possibility is that the bar is not a permanent fixture but a transient, albeit long-lived, phase in the galaxy's evolution. It might have formed relatively recently through a specific and dramatic trigger, such as a close gravitational encounter with another galaxy that has since moved on, leaving no other visible trace. This interaction could have funneled a tremendous amount of material into the central regions in a very short time, sparking the rapid, oversized growth of the bar before the galaxy had time to settle into a more stable configuration. In this scenario, we are seeing NGC 1300 at a special moment in cosmic time, catching its bar in a magnificent but ultimately fleeting state of exaggerated grandeur. Another, more radical idea involves the invisible hand of dark matter. The stability of a galactic bar is intimately tied to the shape and density of the dark matter halo that surrounds it. Most models assume a relatively spherical and smooth halo, but if the dark matter halo enveloping NGC 1300 has a unique, cold, and centrally concentrated distribution, it could provide an additional gravitational scaffold. This unseen framework might act like a cosmic corset, holding the overmassive bar together and preventing it from flying apart under its own immense gravity. The bar's existence, therefore, could be the strongest evidence yet for the specific, lumpy properties of its dark matter halo, making this visible structure a probe for the invisible one that sustains it. The implications of this overmassive bar extend far beyond its own stability. It is the master regulator of the galaxy's energy and material. Its primary role is to act as the galaxy's fuel line, ruthlessly efficient at draining angular momentum from gas and stars in the outer disk and funneling it inward toward the nucleus. This constant torrent of inflow is likely the dominant reason for the strange behavior we see at the galaxy's heart. It could be directly responsible for the clumpy, inconsistent diet of the central black hole, explaining both its general quiescence and its occasional high-energy tantrums. The bar's gravitational torque might also be the orchestrator behind the synchronized bursts of star formation, creating those pockets of co-natal stars by violently compressing gas at specific orbital resonances along its length. This single, overgrown structure is therefore not an isolated anomaly. It is the likely key to understanding a host of other mysteries, the gravitational conductor directing the entire orchestra of the galaxy's chaotic and beautiful evolution. Tucked away within the brilliant star-forming regions of NGC 1300's spiral arms, astronomers have pinpointed a class of stellar behemoths so rare and volatile they are considered the rock stars of the cosmos, luminous blue variable stars. These are not ordinary suns, they are cosmic powder kegs, hypergiant stars boasting masses up to 150 times that of our own sun, and burning with a ferocious blue-white intensity that can outshine millions of solar systems. But in NGC 1300, these stellar celebrities are behaving in ways that break all the established rules, exhibiting eruption patterns and a longevity that directly contradict our best models of how the most massive stars in the universe are supposed to live and die. Their strange activity marks the 22nd profound mystery of this galaxy, offering a front-row seat to the most extreme and poorly understood phases of stellar evolution. The typical life of a luminous blue variable is short, dramatic, and ends in a spectacular supernova. They are stars living on the very edge of stability, so massive that their own immense gravity is barely contained by the outward pressure of radiation from their cores. This precarious balance leads to their defining characteristic, giant eruptions. Every few decades or centuries, a luminous blue variable can undergo a cataclysmic outburst, violently ejecting vast shells of its own outer atmosphere into space. In a single event, it can shed an amount of material equal to the mass of our entire Sun, temporarily doubling its brightness and creating an expanding nebula around itself. These eruptions are thought to be a critical shedding mechanism, a way for the star to lose mass before it reaches its final, explosive end. Yet, when we observe the population of these stars in NGC 1300, their eruption schedules are completely erratic. Some stars that should be in a volatile phase are sitting quietly for far longer than predicted, while others are erupting with a frequency and violence that models simply cannot account for. This erratic behavior forces a fundamental re-examination of the internal physics governing these monsters. One leading theory suggests that the unique environment of NGC 1300 star-forming regions might be creating atypical stars. Perhaps the clouds of gas that gave birth to these blue variables were unusually rich in specific metals or had a unique dynamic, leading to stars with slightly different internal structures. Even a small difference in the way heat is transported from the core to the surface through convection versus radiation could dramatically alter the star's stability and its timeline for eruption. Another compelling idea focuses on rotation. These stars are spinning incredibly fast, and that rotation can flatten them, change how material mixes within them, and even amplify their magnetic fields to incredible strength. A particularly strong magnetic field could act as an internal cage, temporarily bottling up the instabilities that lead to an eruption, only to eventually release that pent-up energy in a far more violent and unpredictable outburst. The implications of solving this mystery stretch far beyond the stars themselves. Luminous blue variables are believed to be the direct precursors to some of the most energetic supernovae in the universe, including hypernova and long-duration gamma-ray bursts. Understanding their pre-supernova behavior is like reading the final chapters of a star's life story. It allows us to predict what kind of death it will have and what remnants it will leave behind. A star that sheds too much mass too quietly might collapse into a black hole with a whimper. A star that erupts violently right before its core collapses could set the stage for a supernova that will be visible across the universe. By decoding the strange patterns of these blue variables in NGC 1300, we are essentially learning to forecast stellar catastrophes, gaining the ability to predict not just if a star will explode, but how and when that earth-shattering event might finally occur. Now, as we shift our focus from the lives of the most massive stars to their final acts, we encounter the 23rd great mystery of NGC 1300, one written in the beautiful, fading glow of stellar death. Throughout the galaxy, astronomers have mapped the location of planetary nebulae, those gorgeous, intricate shells of gas ejected by sun-like stars in their dying breaths. In most galaxies, these cosmic butterflies are found fluttering throughout the disk, their distribution roughly mirroring that of their stellar ancestors. But here, the pattern is bizarrely wrong. Instead of being spread evenly, the planetary nebulae of NGC 1300 are found clumped together in strange, specific pockets that show no correlation at all with the galaxy's current or past star-forming regions. It's as if the elderly population of a city decided to congregate in random industrial parks and empty fields instead of their own neighborhoods, a demographic anomaly that points to a hidden force actively herding these stellar remnants into peculiar grave sites long after their deaths. This peculiar clustering is a profound clue because planetary nebulae are supposed to be excellent tracers of stellar populations. A star must be of a specific, moderate mass to form one, and it takes billions of years to reach that final stage. Therefore, the locations of these nebulae should paint a faithful map of where those intermediate mass stars were born eons ago. The fact that they are gathered in these unexpected clusters, means something has fundamentally rearranged the galaxy's senior citizenry long after they were born. Their current locations are not their birthplaces, and unraveling the mystery of their forced migration is key to understanding the hidden dynamical history of the entire galactic disk. So what powerful, unseen mechanism could be responsible for this stellar gerrymandering? The evidence strongly points to the gravitational influence of the galaxy's most dominant feature, its massive central bar. As the bar rotates, its immense gravity doesn't just funnel gas, it also sculpts the orbits of billions of stars. It creates stable gravitational zones and chaotic regions, much like the orbital resonances that shape the rings of Saturn. It's possible that the stars which eventually become these planetary nebulae have had their orbits dramatically altered over billions of years, slowly herded into specific orbital families and resonance points by the bar's relentless gravitational pull. Their current clustered positions wouldn't reflect their birth sites, but rather the final stopping points of a long gravitational migration, the endpoints of a cosmic conveyor belt they've been riding for most of their lives. There's another, more dramatic possibility: the collective gravitational pull of the galaxy's lumpy dark matter halo. If the dark matter distribution is as uneven and clumpy as the lensing data suggests, its uneven gravitational tug could be creating what are known as gravitational caustics, invisible surfaces in space where stars and their remnants can become concentrated. Over the eons, as stars orbit the galaxy, those with specific energies and angular momenta could be gathered into these folds in the gravitational landscape, creating the very clusters of planetary nebulae we observe today. In this scenario, the clumps are a direct, visible map of the invisible dark matter substructure, a shadow pattern of the hidden mass that holds the galaxy together. Beyond being a fascinating dynamical puzzle, this strange distribution makes planetary nebulae in NGC 1300 an unexpectedly powerful tool for a completely different purpose, weighing the entire galaxy. The technique relies on a principle called the planetary nebula luminosity function. It turns out that for a population of planetary nebulae, there is a consistent upper limit to how bright they can get. This makes the very brightest ones excellent standard candles. No matter where they are, we know their true intrinsic brightness. By measuring how faint they appear to us, we can accurately calculate their distance. But more importantly, by measuring the tiny shifts in their radial velocity using the Doppler effect, we can map how fast they are moving as they orbit the galactic center. This combination of distance and velocity allows astronomers to perform a mass calculation using the same principles that allow us to weigh the Sun by the orbits of the planets. The sheer number and strange distribution of these nebulae in NGC 1300 provide a unique advantage. Because they are clumped, we get multiple, independent mass measurements from different regions of the galaxy's halo, far beyond where most stars can be easily studied. The velocities of these clumps have revealed that the galaxy possesses a far more massive and extended dark matter halo than its visible light would suggest, providing crucial, independent confirmation of the strange results from gravitational lensing. These glowing shells of gas, therefore, serve a dual purpose. They are both the subjects of a mystery and the tools for solving another. Their anomalous clusters hint at a history of gravitational upheaval and rearrangement, while their steady light allows us to take the measure of the very forces that likely shaped their strange journey, revealing the full, hidden weight of the galaxy they call home. And just as the strange distribution of planetary nebulae reveals the galaxy's hidden gravitational history, the very chemistry of its gas tells an even deeper story of its evolution. When astronomers create detailed maps of elemental abundances across the disk of NGC 1300, they uncover the 24th profound mystery. The galaxy's metallicity gradient is not the smooth, predictable decline we expect to see. In a typical spiral galaxy like our own Milky Way, the concentration of heavy elements, everything heavier than hydrogen and helium, which astronomers collectively call metals, decreases steadily as you move outward from the bustling, star-forming center to the quieter outskirts. This makes perfect sense, as the inner regions have hosted more generations of stars, whose supernova deaths have continuously enriched the surrounding gas with these forged elements. But in NGC 1300, this gradient is broken. It features jarring plateaus where the metallicity remains constant across vast distances, and sharp, unexpected jumps where the abundance of heavy elements suddenly plummets or spikes. These anomalies are the chemical equivalent of finding a modern industrial park in the middle of a pristine wilderness, or a primordial forest in the heart of a metropolis, and they force us to completely rethink how galaxies mix their ingredients over billions of years. To visualize this, imagine a detailed map of the galaxy color-coded by metallicity. We would expect to see a smooth transition from hot reds and oranges in the core, indicating high metal content, to cooler blues and purples in the outer disk, signaling more pristine gas. The map of NGC 1300, however, would look wildly different. It would show a chaotic patchwork. Vast swaths of the inner disk might unexpectedly display the blue of low metallicity, like a sudden patch of ancient ice. Meanwhile, isolated regions in the far outer halo could blaze with the orange of high metal enrichment, as if a pocket of the inner galaxy had been teleported to the fringe. These are not minor fluctuations, they are fundamental disruptions to the chemical order, and they point to a history far more dynamic and violent than the galaxy's current, serene appearance suggests. So what could cause such dramatic and specific chemical scarring? Astronomers are investigating several compelling narratives, each with its own profound implications. One of the most persuasive theories involves the late accretion of pristine gas. If vast reservoirs of primordial hydrogen and helium, gas that has never been near a star and is completely devoid of heavy elements, are currently raining down onto the disk from the cosmic web or from the galaxy's own extended halo, they would act as a powerful diluting agent. This influx of pure gas would locally overwhelm the enriched interstellar medium, causing a sharp downturn in the measured metallicity and creating those puzzling plateaus where the dilution is widespread. It would be like a massive freshwater river flowing into the salty ocean, dramatically lowering the salinity in a specific area for a long period of time. Another, more violent explanation points to the galaxy's past mergers. If NGC 1300 cannibalized a smaller, metal-poor dwarf galaxy billions of years ago, the gravitational forces of the merger would have shredded the victim and strewn its stars and gas throughout the halo. The gas from that devoured dwarf, being inherently poor in heavy elements, would not have fully mixed with the richer gas of NGC 1300 even after all this time. Instead, it would persist as coherent streams and clouds, creating those long, coherent regions of anomalously low metallicity that we detect. The merger didn't just add stars, it injected a foreign chemical component that the galaxy has still not fully digested, leaving a permanent metallic fingerprint of its ancient act of cosmic cannibalism. Beyond these external causes, there are powerful internal mechanisms at play. The galaxy's own magnificent bar might be the culprit behind some of the chemical anomalies. As the bar rotates, its powerful gravitational field doesn't just funnel gas inward. It can also drive large-scale circulation patterns, effectively acting as a gigantic mixing spoon for the interstellar medium. This could be dragging metal-rich gas from the inner regions out into the outer disk, while simultaneously pushing pristine gas from the outskirts inward. This churning action would work to homogenize the metallicity, erasing the smooth gradient and creating a more uniform, plateau-like distribution across large sections of the disk. The bar isn't just a structural feature, it's a chemical engine constantly stirring the galaxy's pot and altering its fundamental composition. The tools for this chemical detective work are some of astronomy's most sophisticated. By using advanced spectrographs on telescopes like the Very Large Telescope in Chile or the Hubble Space Telescope, astronomers don't just see these elements, they can precisely measure their ratios. They look at the strength of specific spectral lines for oxygen, nitrogen, and sulfur in the light emitted by H2 regions. The intensity of these lines directly correlates with the abundance of these elements. By doing this for hundreds of regions across the face of the galaxy, they can build a high-resolution chemical map, turning abstract theories into concrete, testable data. A region with strong oxygen lines but weak nitrogen tells a very different story than one where both are strong. And these subtle differences allow scientists to distinguish between gas that was enriched by slow, steady processes and gas that was suddenly polluted by a single, recent supernova. Understanding this broken metallicity gradient is about far more than just mapping elements. It's about accurately reading the galaxy's biography. These chemical scars are a permanent record of the most significant events in its history, its births, its mergers, and its interactions with the vast intergalactic medium. They tell us that a galaxy is not a closed system. It is a breathing, evolving entity that both consumes and is influenced by its environment. The chaotic chemistry of NGC 1300 challenges the old idea of a galaxy evolving in majestic isolation, instead painting a picture of a dynamic structure whose history is written in the complex and uneven distribution of the very elements that make up worlds and ultimately life itself. Woven through the dark halo surrounding the brilliant disk of NGC 1300, so faint they are almost a memory of light, are the 25th strange phenomena delicate tidal streams of stars. These are not the structured arms of the spiral or the dense cluster of the core. They are ethereal ribbons, arcs of stellar luminosity so dim they blend imperceptibly into the blackness of intergalactic space. To the untrained eye, or even to a powerful amateur telescope, these streams are utterly invisible. They are the ghostly signatures of ancient violence, the lingering evidence of a galactic meal consumed billions of years ago, and their detection is one of the most painstaking and revealing pursuits in modern astronomy. Finding these faint streams is a battle against the very nature of light itself. It requires specialized telescopes equipped with incredibly sensitive digital cameras, observing under the darkest, most pristine skies on Earth, or, better yet, from above the distorting effects of our atmosphere in space. The process is one of statistical subtraction. Astronomers take incredibly long exposure images of the region around NGC 1300, collecting photons for hours, sometimes even across multiple nights. They then use advanced software to meticulously subtract the light from all the foreground stars in our own Milky Way, the glow from the Earth's atmosphere, and even the overwhelming glare of NGC 1300's own bright disk. What remains after this meticulous digital cleaning is an astonishingly faint afterglow, the subtle, structured light of these stellar streams, a cosmic fingerprint revealing the galaxy's long-forgotten past. So what exactly are we seeing in these faint ribbons? The leading theory paints a dramatic picture of galactic cannibalism. Billions of years ago, a small dwarf galaxy, itself a gravitationally bound system of perhaps a few 100 million stars, ventured too close to the immense gravitational well of NGC 1300. The difference in their masses was catastrophic for the smaller galaxy. The overpowering tidal forces, the difference in gravity between the side of the dwarf closest to NGC 1300 and the side farthest away stretched it like cosmic taffy. It was not a quick explosion, but a slow, inexorable pulling apart. The stars of the devoured galaxy were not destroyed. They were simply stripped from their original home and scattered along the path of their final orbit, creating these long, thin, and heartbreakingly beautiful rivers of stars that now orbit forever in the halo of their captor. An alternative, though related, explanation suggests these streams might be the remnants of a massive globular cluster that was ripped apart. While globular clusters are incredibly dense, even they have a breaking point when subjected to the repeated gravitational stress of swinging close to a galactic core. Over countless orbits, such a cluster could be progressively shredded, its stars gradually escaping to form a faint but coherent stream that traces its orbital path. Whether the victim was a dwarf galaxy or a massive cluster, the result is the same: a fossilized record of a destructive event, a permanent scar on the face of the larger galaxy that tells a story of growth through merger and assimilation. The significance of these streams extends far beyond their origin story. They are powerful tools for mapping the invisible. The shape, density, and curvature of a tidal stream are exquisitely sensitive to the gravitational field through which it orbits. This means the streams act as probes, tracing out the distribution of mass within NGC 1300's halo, including the vast, unseen envelope of dark matter. A smooth, symmetrical dark matter halo would create streams that are long and relatively straight. But if the dark matter halo is lumpy or asymmetrical, as other phenomena in this galaxy have suggested, it would leave a distinct imprint on the streams, kinking them or causing gaps and variations in their density. By modeling the precise shape of these faint rivers of stars, astronomers can literally chart the invisible geography of the dark matter that dominates the galaxy's mass, turning the ghostly aftermath of a long-ago collision into a precise tool for measuring the cosmos's greatest mystery. Within the sprawling spiral arms of NGC 1300, the violent deaths of massive stars have left behind their own set of bizarre and beautiful ghosts, presenting us with the 26th profound mystery. These are the supernova remnants, the expanding, glowing shells of gas blasted into space by these catastrophic explosions. In most galaxies, these remnants follow a predictable pattern of evolution, starting as a nearly perfect spherical shockwave and gradually becoming more complex as they plow into the surrounding interstellar medium. But here, the remnants are different. They boast strange, asymmetrical shapes and emit energy across the electromagnetic spectrum in ways that defy our standard classifications, suggesting that either the supernova themselves were of an extraordinarily rare type, or that they are expanding into an environment so peculiar it is fundamentally altering their appearance and behavior. One of the most striking examples studied in multi-wavelength data is a remnant astronomers have nicknamed the squid for its bizarre, tentacle-like filaments of gas. In visible light images from Hubble, it appears as a tangled web of glowing, oxygen-rich tendrils. But when viewed through the X-ray eyes of the Chandra Observatory, the story completely changes. The center of the squid glows not with a bright, compact pulsar wind nebula, the expected heart of a typical supernova remnant, but with a faint and strangely elongated cloud of million-degree gas. This disconnect between the optical and X-ray structures is highly unusual. It suggests the original explosion may have been what's known as an asymmetric supernova, where the collapse of the star's core and the subsequent explosion did not happen uniformly in all directions. Instead, the star might have literally blasted itself apart in a lopsided fashion, perhaps due to a powerfully misaligned magnetic field or extremely rapid rotation, hurling the bulk of its material in one predominant direction and leaving behind a bizarre off-center remnant. Another perplexing remnant, catalogued simply as NGC 1300R2, presents a different kind of puzzle. Radio telescopes detect a brilliantly bright, nearly perfect circular shell, classic evidence of a powerful shockwave expanding into space. However, follow-up observations in the infrared with the Spitzer space telescope revealed almost nothing, a profound lack of the warm dust that should have been generated and heated by the supernova blast wave. This absence is deeply telling. It indicates that the star exploded in a region of space that was almost completely empty, a true cosmic void within the galaxy's disk where the density of gas and dust was astonishingly low. The supernova's blast wave had virtually nothing to run into, meaning it couldn't efficiently produce the shocked, glowing dust we expect to see. This forces us to ask what could have cleared out such a large cavity around the star long before it died. The most likely culprit is the star itself. It must have been an incredibly massive Wolf-Rayet-type star, which spends the final million years of its life expelling its own outer layers in a ferocious stellar wind that carves out a vast bubble in space. The subsequent supernova then exploded inside this pre-cleared cavity, creating a remnant that is all invisible shockwave with very little glowing debris, a ghost of an explosion that happened in a room that had already been emptied. The multi-wavelength approach is absolutely critical to solving these mysteries. Each band of light tells a different part of the story. Radio emission traces the whereabouts of high-energy electrons spiraling in magnetic fields, outlining the remnant shock front. Infrared light reveals the warm dust. X-rays map the location of multimillion-degree gas heated by the reverse shockwave that reverberates back into the expanding debris. And optical light shows us the glowing, shocked filaments where the expanding shell slams into cooler, denser clouds of interstellar gas. By combining these views, astronomers can perform a kind of cosmic forensics, reconstructing the exact conditions of the star's death and the environment it died in. A remnant that is bright in radio and X-rays but faint in infrared points to a low-density environment. A remnant that is highly asymmetrical in X-rays but symmetrical in radio suggests a profoundly asymmetric explosion. These strange morphologies are not just curiosities, they are the key diagnostic tools that allow us to classify the very nature of the explosions that created them. The implications of these unusual supernova remnants are immense. They act as a direct record of the death of massive stars, which are the primary engines of galactic chemical evolution. It is in these titanic explosions that elements like iron, oxygen, and silicon are forged and then scattered into space, eventually to be incorporated into new stars, planets, and even living organisms. If supernova in NGC 1300 are frequently occurring in unusual ways or in strange environments, it means the recipe for spreading these essential elements is different here. The galaxy might be enriching its interstellar medium in a more chaotic, uneven fashion than our own, potentially leading to the bizarre chemical anomalies we see elsewhere. Furthermore, these strange remnants could be the signposts pointing toward even more exotic stellar deaths, such as the pair instability supernova of the universe's first stars or the collapse of stars directly into black holes with no visible explosion at all. Each oddly shaped shell of gas is a fossilized moment of cosmic violence, and by deciphering their forms, we are reading the final, dramatic chapters in the lives of the galaxy's most massive stars. But the galaxy's gravitational story may have yet another hidden character, one whose presence is felt everywhere but whose face remains utterly unseen. The 27th profound phenomenon in NGC 1300 is the compelling and controversial evidence for a hidden companion galaxy, a small, dark matter-dominated satellite that seems to be gravitationally tugging on its massive spiral neighbor, yet has somehow escaped every attempt to find it with optical, infrared, or ultraviolet telescopes. This isn't just a case of a faint object being overlooked. It's the possibility of an entire galaxy that is so fundamentally different, so dominated by invisible matter, that it barely emits any light at all. A ghostly cosmic partner whose existence is inferred solely through its gravitational influence on the motions of stars and gas within NGC 1300 itself. The primary evidence for this unseen companion comes from a foundational technique in astronomy, the construction of galactic rotation curves. By using spectrographs to measure the Doppler shift of light from stars and hydrogen gas at different distances from the center of NGC 1300, astronomers can plot a graph of how fast material is orbiting versus its distance from the core. According to Kepler's laws of motion, we would expect stars in the outer disk to orbit more slowly than those near the center, just as Pluto moves more slowly around the Sun than Earth does. However, like most galaxies, NGC 1300's rotation curve stays flat far out into its disk. The outer gas clouds are orbiting just as fast as the inner ones. This was the original clue that led to the dark matter hypothesis, proving the galaxy is embedded in a massive, invisible halo. But for NGC 1300, the story doesn't end there. The curve isn't just flat, it shows specific, small-scale anomalies, tiny wiggles and deviations from a perfect smooth line. These subtle bumps and dips in the velocity data are the gravitational fingerprints of something else, a localized mass concentration tugging on the galaxy's disk and imparting a slight but measurable perturbation to the orderly rotation. To decipher what could create these specific gravitational ripples, astronomers turn to incredibly sophisticated computer simulations. They create a virtual model of NGC 1300, complete with its visible disk, central bar, and a standard smooth dark matter halo. They then set it rotating and let the laws of physics play out. In most cases, the simulated rotation curve is smooth. But when they introduce a small, dense, and invisible perturber into the simulation, a satellite galaxy made almost entirely of dark matter, orbiting a few 100,000 light-years from the main disk, the virtual velocity data begins to develop those exact same small-scale wiggles. The match between the simulation and the real-world observations is uncanny, strongly suggesting that the anomalies in the rotation curve are not random noise but the clear signature of a massive, unseen object on a specific orbital path. The simulations can even begin to constrain the properties of this ghostly companion, suggesting it might have a mass of several billion suns, yet be so devoid of stars that its light output is almost zero. So what kind of galaxy could possess such immense gravitational clout while remaining virtually invisible? The most likely candidate is a type of object that has become a holy grail in astrophysics, a dark galaxy. Predicted by some models of dark matter structure formation, a dark galaxy would be a gravitational-bound halo of dark matter that simply failed to accumulate enough normal gas to form a significant number of stars. It would be a cosmic underachiever, a place where the conditions for star formation never quite aligned, leaving it a vast sphere of pure, invisible mass. Alternatively, the companion could be a dwarf spheroidal galaxy that was once slightly brighter, but had its gas the fuel for star formation, stripped away billions of years ago during a close encounter with NGC 1300. What remains would be a skeleton of a galaxy, a collection of a few ancient, faint stars held together by a massive cloak of dark matter, making it incredibly difficult to detect against the blackness of space. The hunt for this object is ongoing and immensely challenging. Astronomers are using the most sensitive telescopes ever built to conduct deep, wide-field surveys of the region around NGC 1300, searching for any faint smudge of light or an unexpected clustering of a few dozen ancient stars that might betray the companion's location. Others are looking for more indirect evidence, such as a specific pattern of disturbances in the delicate tidal streams of stars we've already discovered in the halo, which would be affected by the gravity of a passing satellite. Confirming the existence of such a dark matter-dominated companion would be a monumental discovery. It would provide stunning proof that dark matter can indeed form structures all on its own, and it would force us to revise our census of the galactic population of the universe, suggesting that for every bright galaxy we see, there could be numerous dark ones lurking unseen, shaping the cosmos through gravity alone. And now we turn to a phenomenon that relies on the universe itself acting as a magnifying glass, revealing objects that are otherwise completely undetectable. The 28th profound mystery in NGC 1300 involves a series of peculiar and fleeting events known as microlensing. This process occurs when a dark, compact object like a black hole, a neutron star, or a brown dwarf passes directly between our line of sight and a more distant star in the galaxy. According to Einstein's theory of general relativity, the gravity of this foreground object warps the fabric of spacetime around it, bending and focusing the light from the background star like a lens. From our perspective, this causes the distant star to temporarily brighten, often by a significant amount, before fading back to its normal luminosity as the lensing object moves out of alignment. It's a tiny, precise flash of light, a cosmic blink that can last for hours, days, or weeks, and in NGC 1300, these events are happening at a rate that far exceeds all predictions, suggesting a hidden population of dark, massive objects weaving their way through the galaxy's spiral arms. Detecting these incredibly subtle events is a monumental task that requires a specific kind of astronomical survey. Projects like the Optical Gravitational Lensing Experiment, or OGLE, and the Massive Compact Halo Object Project, known as MACHO, are dedicated to this very purpose. They don't use massive telescopes to take pretty pictures. Instead, they employ wide-field cameras to image the same dense star fields in the direction of galaxies like NGC 1300 night after night for years on end. The resulting dataset is not a collection of beautiful portraits, but a colossal library of photometric measurements, precise records of the brightness of millions of individual stars over time. Powerful computers then analyze this data, searching for the distinct, symmetric light curve that is the signature of a microlensing event, a smooth, predictable rise to a peak in brightness followed by an equally smooth and symmetric decline. Finding one of these signals is like finding a single, specific fingerprint on a planet covered in sand, a testament to both the patience of astronomers and the power of modern data analysis. The sheer frequency of these events in NGC 1300 is what makes them so puzzling. Based on our current understanding of the galaxy's mass and the expected number of dim stars like white dwarfs and brown dwarfs, we simply should not see this many microlensing flashes. The high rate points to an overabundance of a specific type of lensing object, massive compact halo objects or MACHO. This term encompasses any large, dim body that can cause a lensing effect without emitting significant light of its own. The leading candidates are stellar mass black holes and neutron stars, the remnants of massive stars that died in supernova explosions. The data suggests there could be a vast number of these dark remnants roaming the galaxy, far more than our models of stellar evolution predict should exist. It's as if NGC 1300 has a hidden army of stellar ghosts, the invisible skeletons of its past, silently drifting through the darkness and revealing themselves only by the way they bend the light of others. But there is another, even more exotic possibility. Some of these lenses might not be stellar remnants at all. They could be primordial black holes, hypothetical objects thought to have formed from extreme density fluctuations in the first moments after the Big Bang. These would not be the product of a dead star, but ancient relics from the birth of the universe itself. If a significant portion of the galaxy's dark matter is made up of such primordial black holes, it would neatly explain the excess number of microlensing events. Each detection would then be more than just the discovery of a dark object. It would be a direct probe into the very nature of dark matter and the conditions of the early cosmos, a window into a chapter of universal history that has been closed for over 13 billion years. Every single microlensing event is a treasure trove of information because the specifics of the light curve allow astronomers to calculate the mass of the object causing it. The duration of the brightening event tells us about the lens's transverse velocity, and the precise shape of the curve reveals the alignment and the mass. This means we are not just counting these dark objects, we are effectively weighing them one by one, building a mass function for a population of things we cannot see. The results from NGC 1300 are building a picture of a galaxy that is teeming with unseen mass in the form of compact objects, a finding that could force a major revision of our theories about how many stars end their lives as black holes and what truly makes up the dark matter that holds the universe together. Each tiny, temporary flash of light is a profound message, a brief signal from the darkness that speaks volumes about the true, hidden structure of this magnificent island of stars. And just as we're grappling with the implications of the galaxy's hidden dark objects, we encounter a mystery that strikes at the very heart of how we measure the cosmos itself. The 29th profound phenomenon centers on NGC 1300's blatant refusal to comply with one of astronomy's most trusted rules, the Tully-Fisher relation. For decades, this relation has served as a fundamental yardstick for the universe, providing a remarkably consistent link between a spiral galaxy's rotation speed and its intrinsic luminosity. In simple terms, the faster a galaxy spins, the brighter it should be. This makes intuitive sense. A more massive galaxy has more stars to glow brightly and also possesses the stronger gravity needed to whip those stars around at higher speeds. It's a beautifully elegant correlation that has allowed astronomers to estimate the distances to far-off galaxies with incredible accuracy, essentially turning them into standard candles for measuring the vast expanses of the universe. But NGC 1300 is an outlier. Its rotation speed, meticulously measured from the Doppler shifts of its hydrogen gas, is far too high for its observed luminosity. It's spinning like a massive, brilliant giant but shining with the light of a far more modest galaxy, creating a glaring inconsistency that forces us to question our most basic assumptions about distance, mass, and the very structure of spiral galaxies. To understand why this deviation is so disruptive, imagine using a car's speedometer to reliably guess the power of its engine. For most cars, this works. A car going 200 kilometers per hour almost certainly has a more powerful engine than one puttering along at 50. Now picture finding a compact car that somehow rockets down the highway at 200 kilometers per hour while sounding like a simple 4-cylinder engine. You would immediately question your understanding. Is the speedometer broken? Is the engine secretly modified? Or is there some hidden mechanism, like a hidden turbocharger or an unseen tow rope providing the extra power? This is the precise conundrum presented by NGC 1300's Tully-Fisher anomaly. The galaxy's rotation speed, our cosmic speedometer, is telling us it possesses a tremendous amount of mass and gravitational pull. But its luminosity, our measure of its stellar engine, suggests a much smaller, less powerful system. This discrepancy points directly to the presence of unseen mass, a colossal amount of it, that contributes to the gravity but not the light. While this is the classic signature of dark matter, the scale of the deviation here is so pronounced that it suggests something may be fundamentally different about how dark matter is distributed in this galaxy, or perhaps even how the relation itself functions in barred spirals. The implications of this single galactic outlier ripple outward to affect our understanding of the entire cosmos. The Tully-Fisher relation is not just an interesting curiosity. It is a critical rung on the cosmic distance ladder, the sequence of methods astronomers use to measure the scale of the universe. If this relation is less universal than we thought, if certain types of galaxies, like barred spirals, systematically deviate from it, then any distance calculation based on it could be significantly flawed. This means our estimated distance to NGC 1300 of 61 million light-years itself could be called into question. If we've misjudged its distance, we've also misjudged its true size and luminosity, creating a cascade of errors in our understanding. Furthermore, this anomaly forces a critical re-evaluation of galaxy formation models. Perhaps the unique evolution of a barred spiral, with its strong funneling of gas inward, leads to a different efficiency in converting gas into stars, resulting in a galaxy that has built a powerful gravitational framework but has not yet filled it with a proportional number of shining stars. The galaxy's bizarrely oversized bar, which we've already explored, could be the central culprit, its immense mass contributing enormously to the rotation speed without adding equally to the overall starlight, permanently throwing off the Tully-Fisher balance. Resolving this mystery requires looking at the galaxy through every available lens. Astronomers are cross-referencing the rotation speed with other methods of estimating mass, such as the motion of its globular clusters or the gravitational lensing effects we discussed earlier. They are also creating increasingly sophisticated computer simulations to model the formation of barred spirals, trying to see if they can naturally produce a galaxy that matches NGC 1300's specific combination of rapid rotation and relative dimness. Each piece of data is a crucial constraint, helping to determine whether this is a strange exception that proves the rule or a sign that our cosmic rulebook needs a significant new chapter. The galaxy's stubborn defiance of this fundamental relation is a powerful reminder that our tools for understanding the universe are based on patterns we observe, and whenever an object comes along that breaks those patterns, it forces us to look deeper, think harder, and ultimately expand our knowledge of how the cosmos truly works. And this brings us to our final and perhaps most humbling mystery, one that forces us to look at this magnificent galaxy not just as a collection of physical phenomena, but as a potential home. Despite its grand design, its vast reservoirs of raw materials, and its billions of suns, NGC 1300 has responded to our most earnest searches with a profound and unsettling silence. In the decades-long endeavor known as the Search for Extraterrestrial Intelligence, or SETI, astronomers have tirelessly trained radio telescopes on promising star systems, listening for any artificial signal, a narrow-band transmission, a powerful pulse, any pattern that breaks the natural chaos of cosmic noise and shouts, "We are here." This galaxy, for all its wonder, has offered nothing but the natural radio whisper of hydrogen gas and the crackle of distant supernova. It is the 30th and perhaps most philosophical strange phenomenon, the great silence from a place that, by all accounts, seems to have every ingredient for life to arise. This lack of a detected signal forces us to confront some of the most profound questions in all of science. The first possibility is simply that we are alone, at least within the scope of our observations. NGC 1300 may indeed be a cosmic desert when it comes to intelligent life. This idea is encapsulated in the Fermi paradox, which starkly contrasts the high probability of intelligent life emerging somewhere with the complete lack of any evidence for it. Perhaps the evolution of technological civilization is not a natural or common outcome of planetary evolution. It could be that life itself is relatively common, but the journey from single-celled organisms to a spacefaring species is littered with cosmic filters, catastrophic events like asteroid impacts, self-inflicted disasters like nuclear war or ecological collapse, or simply the immense difficulty of maintaining a stable civilization for the thousands of years necessary to develop interstellar communication. In this scenario, NGC 1300's silence is a somber message, a warning that the universe, for all its beauty, might be inherently hostile to intelligence lasting long enough to make its mark. But there is another, less bleak interpretation. Our assumptions about what to look for, or even where to look, might be hopelessly naive. Our current SETI strategies are overwhelmingly biased by our own technological adolescence. We primarily search for radio signals because that was our first major form of long-distance communication. But what if a truly advanced civilization has moved far beyond radio, using technologies we cannot yet conceive of, like neutrino-based communication or something that manipulates the fabric of spacetime itself? Their signals would be completely invisible to our current arrays, rendering their presence undetectable. Furthermore, our concept of a habitable zone is incredibly Earth-centric. We look for planets orbiting at a distance from their star where liquid water can exist. but life could be based on entirely different chemistries, thriving in the methane lakes of a freezing moon or in the subsurface oceans of a rogue planet drifting between the stars. Our narrow search parameters could be causing us to miss a galactic community teeming with life that is simply too alien for us to recognize. The silence from this beautiful barred spiral might also be a function of time. Civilizations, even long-lived ones, may only broadcast detectable signals for a vanishingly brief window in a planet's billion-year history. Imagine a species that uses powerful radio transmissions for a few centuries before transitioning to a more efficient technology, or one that chooses to deliberately go quiet to avoid attracting attention, a concept known as the zoo hypothesis. The odds of our brief sliver of technological existence overlapping with another civilization's equally brief broadcasting phase across a gulf of 61 million light-years are astronomically small. We could be listening to a galaxy full of ruins and relics, the static-filled graves of civilizations that rose and fell millions of years ago, their signals having already washed over our world when humanity's ancestors were still climbing trees. Ultimately, the great silence from NGC 1300 is not an end to the conversation, but a beginning. It is a blank canvas upon which we project our hopes, our fears, and our deepest questions about our place in the cosmos. This majestic island of stars with its quiet heart, its ghostly magnetic fields, and its missing clusters now adds one final, resonant mystery to its ledger. Its silence is a powerful reminder that the universe is under no obligation to conform to our expectations. It challenges us to become better listeners, to develop new ways of seeing, and to continue the search with a humility matched only by our curiosity. For in the end, the unanswered question might be the most important one of all, driving us to explore further, to think deeper, and to never stop wondering what other secrets the darkness holds. From the profound silence of its central black hole to the ghostly whispers of its radio loops, from the clumpy, unseen grip of its dark matter halo to the chaotic and contradictory nursery of its central bar, NGC 1300 has proven itself to be a galaxy of endless wonder and relentless contradiction. We've journeyed past high-speed hydrogen clouds that defy gravity's pull, stared into the cryptic infrared glow of hidden power sources, and puzzled over spiral arms that refuse to be symmetrical twins. We've witnessed the periodic X-ray tantrums of a dormant giant, felt the immense pressure of its magnetic fields, and traced the faint, ancient rivers of stars that tell a tale of galactic cannibalism. We've uncovered populations of stars born in synchronized bursts, searched for missing clusters of ancient suns, and decoded the abnormal chemistry of its nebulas that suggests a history written in violent mergers and quiet accretion. We've analyzed the rapid flickering from its core, mapped the inexplicably hot and cold dust clouds, and felt the force of stellar winds that both give life and bring death. We've catalogued bizarre binary systems, listened for the faint gamma-ray hum of dark matter annihilation, and observed the warped outer disk that hints at an unseen gravitational dance. We've been baffled by mysterious, repeating radio pulses, contemplated the stability of an overmassive bar that shouldn't exist, and been captivated by the erratic behavior of hypergiant stars. We've followed the strange migratory patterns of planetary nebulae, diagnosed the peculiar remnants of supernova explosions, and even searched for the gravitational signature of a hidden, dark companion galaxy. We've counted the fleeting flashes of microlensing events that reveal a hidden population of dark objects, and we've been humbled by the galaxy's defiance of a fundamental cosmic relation, the Tully-Fisher law. And finally, we've sat in the profound silence of its unanswered potential, the great quiet that speaks to our deepest questions about life and our place in the cosmos. Each of these 30 phenomena is more than just a strange fact, it is a direct challenge, a challenge to our textbook definitions of how galaxies live and evolve. A challenge to our models of star formation, stellar death, and the very nature of matter itself, NGC 1300 doesn't just ask us to add new paragraphs to our understanding, it asks us to rewrite entire chapters. It shows us that a galaxy is not a static painting but a dynamic, breathing entity, a complex system where gravity, magnetism, radiation, and time intertwine in ways we are only beginning to comprehend. This journey doesn't end here. It continues every time a new telescope turns its gaze toward this cosmic whirlpool, every time a researcher runs a new simulation, and every time someone like you looks up at the night sky and feels that spark of curiosity. The universe is filled with mysteries waiting to be unraveled, and NGC 1300 is a stunning reminder that the greatest discoveries often lie in the details, in the anomalies, and in the things that simply don't fit. So we want to hear from you. Which of these 30 strange phenomena captured your imagination the most? Was it the silent black hole, the possibility of dark matter annihilation, or the great silence that speaks to the Fermi paradox? Let us know your thoughts in the comments below. We love diving into these discussions with you. And if you're ready to continue exploring the wonders of the cosmos, make sure to subscribe and hit the bell so you don't miss our next journey into the depths of space. The universe is strange, beautiful, and endlessly surprising. Let's keep discovering it together.